what we will do today, okay, I am supposed to speaking about data structures, very important, okay? So I want to speak about briefly about those data structures, okay? Some are obvious, some may seem obvious, but they are not, okay? And once that is done, I will pass the word to Kratos, who will speak first about search data structures, so things you can use to find what is close to what else, let's say. And then we'll speak about things related to Kratos, to the internal organization of Kratos. So a bit on the continuation of what I was doing yesterday. Again, it needs to be interactive, so please do stop me. I will try to make the questions to ensure you're not falling asleep, or if you're asleep, you get awoken. Okay? Then, a vector. What is a vector by definition? A vector is a succession of numbers which is consecutive in the memory. Okay? Now, this is pretty obvious, we may agree. There is just one thing that you must know. Vector. And this is actually something that is true for a vector, but is also true for all of the data structures, essentially. And it is, what do I know? What do I know at compile time? Why am I telling this? Because there are essentially two options. I may know the size of this vector at compile time, or I may not know the size of this vector at compile time. And the other thing is, when I do a loop over that vector, do I know the features of this loop at compile time, or will I have, the kind of loop, the way I look through the vector will depend on information that I only know when I run the loop.
That's related to dynamic memory.
It is related to dynamic memory, but not just. Okay. So let's say option one, size known. Size known at compile time. Okay, if you know the size at compile time, then you may instruct the compiler to allocate it on a certain kind of memory. It will be allocated on stack. Allocated on stack memory. The allocation onto the stack is managed by the compiler, and it is a very fast allocation because the stack is a portion of the memory that is already pre-allocated, and it's a stack. So it's a pile to which you add things. Okay, it is very fast to add there. So it has essentially no cost to allocate memory there. Okay. There is a limited amount, and the point is that you need to know it at compile time. Is there any other advantage of knowing something at compile time? Well, if you know something at compile time, the compiler can do a lot of optimization that otherwise are simply not known. For example, it can reorganize the way in which you go through in which you write your loops. It can do so in order to minimize the calculations that it does, or in order to better use its internal structure. We will speak a bit more of this tomorrow. Do you know any in C++? C++, okay, so not in C, that would be double and then the size with the known size. In C, you would allocate as I think, how is the syntax? Double X, is it like this, the syntax? I never use this. I should be this one, okay? So in this case, you're telling allocate onto the stack a consecution of 3 doubles, for example. In C++, do you know what is the class that does this? Sorry?
Array.
That's the std array. That's correct. So it is std array, double 3. The difference is that for this array, you must know that the size is 3. So it is something you must remember. While this array has the information that it has 3, that the size is 3 available. So you can ask, so std array double 3x. Okay? To this, you can ask for x.size, and statically, at any point at which you need it, to know that the size is 3. Okay? But this is something, information in both cases available to the compiler. In Kratos is older than the standard in which this was added. Okay, so you can use as the array, but we have dense vector double 3 3x or array 1D. That's exactly the same thing. There are two names for the same thing. The hint is whenever you can, if you know the size or if you can make an effort to know the sizes, always use stack allocated array. You interrupt me if I tell something wrong.
Okay? If you don't know the size and you more or less have a hint, please allocate more memory than you need, but let's be static.
It makes the time for allocation is enormous on a modern machine. Okay? But then there is the option 2.
Sorry, Ricardo, the exponential is array/1. I can see it.
Array underscore 1b. It's an underscore. That's in Kratos. That's Kratos specific. Actually, that's useless. Okay? The point is, one of the big disadvantages, still big disadvantages of C++ with compared to other languages is there is no matrix class, for example, and the vector classes were updated pretty recently. I mean, well, recently it means in the last 15 years, okay? That's okay, we can discuss if that is recent, okay? I agree. So option 1, option 2. Size known at runtime. Well, there is no other option that dynamic allocation. And about this, we could also put some asterisks. Well, dynamic allocation is a modern feature. It was not there maybe 25 years ago, okay? 20, I don't know. I mean, you can see all the memory, but all the memory has spots because you can, it's not all contiguous. You can allocate something here, then allocate something here, then deallocate this. And then someone in charge, the memory allocator, if you ask for some amount of money, for some amount of memory, it will give you the best chunk available, which has the length that you may have. So memory is fragmented. It has a cost to look for where you want to allocate the memory. And all of this is an impact. So it takes time to allocate memory dynamically, in particular, a lot of small arrays or very large arrays. In C, again, now I never use C as such, but it is, how is that? Double mu, no. x, how is that? Double x equal. No, yes, the STD vector I know. Double x equal to new double 3, something like this. Something like this. No, how is it the allocation? Allocate an array dynamically of size 3. I don't remember the syntax exactly. No, STD vector, no. I don't want STD vector in C++. No, you can also use new. There is a syntax for new. Okay, I don't remember the exact syntax for this, so I don't. Okay, this is C. It's not C++. Okay. In C++, I mean, I can look for it, or you can look in stack. There is a way of doing it like this in C, or with malloc, as he's saying, but also with new. In C++, std vector double 3, and here, I mean, okay. No, you're right. Without the 3, I made it wrong. Double. That was red. X 3. You can do this, or you can do double allocate it and then do resize. How much memory does that vector occupy? How many bytes?
Nothing until you use it.
No. If you do this x3, you're allocating it, and you're even setting it to 0. That's what the standard tells. Setting it to 0 is a cost, because it means that you look through the vector and you set it to 0. Okay? So, no. This 2 is allocated to 0. But anyway, allocated, set to 0 construction. Here I should put a few remarks. Okay. So how many doubles? How many bytes? First of all, one double, it's 8 bytes. Okay. So imagine that I want to locate a vector of 3 STD vector which contains 3 doubles. Answer, how many bytes? Smart, but wrong. Well, I mean, anyway, I'm not, I just want, I mean, the reason for which I'm making this is not to make fun of you, is because it's not 24, it's not just 3 doubles. This is a dynamically allocated array, which at any point within your program also allows you to do x.size, and it will tell you what is the size, okay? So as a minimum, it will have to store the size of the vector, the 3. How much does an integer occupy? If you write, well, that's correct, that's an integer. But this one allocates an STD size t. An STD size t occupies 8 on 64-bit machines. Okay? So we are already at 32. Do you think it occupies 32? It doesn't, because what it does, and this is really the feature that, I mean, if you need 3, these are the 3 you need, it will allocate a bit more. Well, that is supposed to be pointed, okay? So this is empty. This is not initialized. Okay, let me use a different color, okay? So it will allocate a few slots more. How many depends on the compiler. It's not prescribed. Why? Because it is an array that is to which you may append things, okay? And dynamically you can push back and it will grow. But to do this, it allocates a bit more of memory.
So this kind of vector is rather similar to the append in Python, for example.
it's very similar to the append in Python. Actually, if you can take x empty and push back to it, and it will grow in size. Reallocating for you, it's transparent, okay? It will reallocate, it will behave as a list, more or less.
Exactly as it is.
As a stack more than a list.
Yeah, but the problem is that every time that you have to allocate and selecting the size is important, it's going to be super inefficient because it has to take all the vector. If it doesn't fit in the chunk of it that it's allocated, it will copy the whole thing to another place, it will copy that, allocate all that place, and deallocate all the things that you have allocated.
So
Super inefficient.
this is the reason for which I wanted to speak about vector, because you say it is obvious. Well, you need to be aware of those things, okay? So how much memory it will occupy? It will occupy, sorry.
One question. You said 24 bytes for the doubles, and then the 8 bytes that you added were coming from where?
For the size.
For the size of like
The size of a vector, I mean, the maximum amount of memory you can allocate is very large on a 64-bit machine. So in order to index it, it's not enough with an integer. You need an STD size t, because it could be enormous, this array. So they allocate a 64-bit size in order to. But this is wrong, because now, look, this wrong. I mean, this is not enough, because now, aside from having allocated, I'm gonna say 6, okay, because you have those empty ones, and I don't know how many there will be. It will depend on your compiler, okay? I also need to know what is this length here. So this is size, okay, and this is capacity. It is called like this in the library. It is the amount of memory that is actually allocated for the vector, for the data in the vector, okay? Well, capacity is another STD size t. It is larger than size, so it has to be, so as a very minimum, you will need size, capacity, and the number of doubles times capacity. So it's not, if you're allocating 3, maybe you're allocating 8 times 8 bytes, okay? So there is a big overhead in doing this, okay? That's more or less. There are ways to minimize it. For example, the STD vector as a function that is shrink to fit is called like this, which makes the capacity to coincide with the size, okay? And then it can still grow. It also has some nice features. I mean, this is a very powerful container, okay? One of the things is that apart from double, here you could put another argument. And the other argument is allocator. So you could tell or build into the same type how you allocated that. For example, you could use your own allocator, or you may tell to allocate it in the stack. So there are allocators out there that essentially reserve memory on the stack, and then they do allocation in there. These are faster, but they are also more risky because the memory that you have on the stack is not encrypted. Okay? And those allocators also control what you do at construction time, so it is possible to write an allocator that does not do the zero initialization. Okay? Sorry?
Which allocator do you use normally?
The standard one of STD. I'm just telling that this exists, and it is part of the type.
In Windows, if you want to go very large program, we use an Excel allocator. Because the standard one does not work. I mean,
It's extremely slow. In the worst case performance is very better.
It's like 12 hours versus 3.
So yes, for example, the Intel TDD, or there are a few libraries that provide optimized allocators, which you can replace. In Kratos, you have, well, vector. vector double, which, I mean, that would be vector double x3, okay? This occupies 3 doubles plus the size, okay? But on this you can push back, on this you cannot push back. So this you can resize, but it is on you to do everything, okay? For the ones that will not work in Kratos, this is still important. It's very important. You need to be aware of this because it has a big impact in performance. It's in performance and in memory, okay? Anyway, the second thing now is matrix, because matrix, of course, it is more complicated than vector. Well, so option 1, size known. At compile time. Well, in C, that is double x 3, 3. I think the syntax is this one, right? The syntax is, I think it is this, okay?
Yeah,
It is this. The other one was double asterisk equal to new double.
a new
C.
double X.
No, but this,
yeah.
yeah, okay. The other one, sorry, I don't just, I will not write how to locate it with the new because I don't remember, okay? That's, I never use it. In C++, how do I locate a matrix in C++? Standard C++. Answer, you don't. There is no matrix class in C++, okay? So in C++, you can use the C, that's of course possible, but there is not a matrix as such until C++ 23, which is not 26, sorry, which is not there, okay? In C++ 26, they are adding it. In C++ 26, so in the next future standard, there will be MD array. Okay, which is double, and then you have to say the extents. The extents will be either dynamic or static. Okay, extent 1, extent 2. Okay, this is something. I mean, that's for the future. It's not there. We are discussing the details of this. Okay, in Kratos. This is bounded matrix, double 3, sorry, double 3, 3.
To make it a little bit bigger. No. It's very tiny.
This is something that we inherit from UBLAS. So how much do you think you should occupy this?
9 times 8.
9 times 8, that's correct. And the size 1 and size 2, so row size and column size, do you need an annotation for this? So it is static, it is known as compile time. So the compiler could do it. Unfortunately, the library that we use is when we implement and store them. It's not needed, it shouldn't be this way, but the library we are using right now stores size 1 and size 2, so there is an overhead of 2. Okay? This is what we use right now is U+, and we eventually want to change once it comes into the standard, but that's not an easy thing. Option 2. Dynamic. So runtime. In C, I don't know, I don't remember. We can check, but this is really your first Google search will find this. In C++, there is not. Again, this will be MD array double dynamic extent. But this is not available right now. We are discussing to how to standardize this. So right now it is not there in Kratos. You have matrix. Okay. There are others. The eigen has other, so it has its own, is a library that provides those, and there are a few at least libraries that implement this. Now, this has the same, occupies the size, so what you need for the memory plus what you need for the size 1 and for the size 2. Okay, there is no way, no escape from that. Okay. Now, there is also something that you need to understand because it's very important. Okay, imagine that I want to do I have a matrix A, and I want to multiply it by a vector X. Okay. Let's imagine even that I know the sizes of A and X. A is 3 by 3, and X is 3. Okay. So this is of size 3 by 3, sorry. This is of size 3. Okay. Now I'm gonna do the multiplication. So how would it be? For unsigned int I equal to 0, I lesser than A dot size 1 plus I for blah 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 J, for J lesser than A dot size 2. That's a dot, okay. Plus J. And then you would do, well, this is, let's say, Y equal, okay? Then you would have Y I equal to A, sorry, I J times X J. So let me correct because I'm not doing it right. A I J X J. This is a round parenthesis. This is a square parenthesis. Why so? Because until C++, not sure if 20 or 23, you could not use a square parenthesis for multi-index access. Okay, it was not there. Now it is there, but it is there just if you have the very latest standard. Okay. So for the time being, we are still using the round parentheses. Okay. Now, what do you think that happens like this under the hood? So what the compiler does when you write AIJ? I mean, the question is, how is the memory allocated? So how is the matrix allocated into the memory? So this under the hood will be translated into something like line, okay? So my term I need to make it a bit smaller because otherwise we see nothing, is equal to a dot data dot begin. This is the pointer to the first entry in the matrix. So that's a pointer. I mean, plus how is it? Size 1 a dot size 1 times I times plus j. Okay, I'm sure I'm not explaining it well. Let me try to imagine that your matrix is the following: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is your matrix. Okay. In the memory, this is stored as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Where, I mean, this would be where the first line ends. So if you are telling that I want this, which is third row, second column, you will have to shift from the beginning of this amount 3 times, I mean, plus this. Okay? This operation has a cost. It's an integer multiplication, but it has a cost. Okay? And this cost is not for free. So it's a cost that you pay when you do any operation with the matrices. You understand what I mean or not? You can tell no. No. Sorry, but I mean, the IJ needs to be flattened, so you need to multiply it by the row size. Do I have any advantage in the stack, sorry, in the compile time versus run time? If my matrix is known, all the sizes are known at compile time, then size 1 and size 2 are known at compile time. Then the compiler, particularly if the size is small, may completely take out this loop, unroll the loop, transform into something in which I pre-compute at compile time all of those calculations. Okay, this would allow to save a lot of calculation and then to have faster.
Probably just take the value.
Take the value, so that the value is there. Okay, saving the intermediate calculation. This is just an example, and maybe it is a stupid one. But what I'm trying to tell is that the more information that you give to the compiler, the more the compiler can do magic for you, magic that you don't know, but is there under the hood. Okay? So you do want to inform the compiler as much as you want of, right? I'm always looking at Charlie because he knows more than I do on this, okay? So that's obvious. So now we spoke about vector and we spoke about matrix. In there, I also put map, what, set and map. And really
So
set.
I have a question.
Yes.
When you don't know the exact size of a vector or a matrix, is it better to allocate it in excess or go for dynamic division?
clean coding tell to use STD vector, let's say. So, I mean, you don't want to deal with the details about the allocation. That gets very nasty unless you really need because it's in the.
I would say that it's a compromise. If you're working with a matrix character of like you're not looking for million or thousand million, do it if you know that it's between, I don't know, 1% or 1% more and 1% less of a number that you know, do it statically.
I mean, if you can do it statically, the performance is better.
If you absolutely no idea of what is going to be there, then maybe.
But sorry, one important thing. Even if you know that it will not exceed 100, but you don't know the exact size, the compiler already cannot do that because the size is not known at compile time. And it will not do operation onto things that are not there, right? So what I'm trying to tell is, his answer is correct. And also depends on where you are. If you are in the innermost loop of the where you need absolute performance, then pay any price, right? Any coding price. Otherwise, clean coding or understandable coding is very important. Okay, that's the that said, whatever answer is correct. Okay, so that's a bit of a compromise as it stands. Okay, I just want to say. And I need still maybe a quarter of an hour, but I want to say set and map, and then maybe an ordered set and ordered map. Okay? Do you know what is a set? A set is a list of unique elements. So, example, you take 1, 2, 1, 4, 3, 3, 2, okay? If you have a STD set in particular, STD set, it is an ordered list of unique value. Order, I miss the order.
It's like the numerator.
No.
No.
The numerate is a list, is a way to assign keys to certain variable names, let's say. But it's something you do at compile time. This is done at runtime.
So you could enumerate a set, but by itself is not a
So imagine that this is your data. You pass this to construct a set. What you obtain in the set is something that looks like 1, 2, 3, 4, even if you add them in this order. Because a set, at least, it is an ordered set, the one that is in C++. Okay? What does it mean? There is no repetition, so that's an important thing. It helps you. And there is an ordering. So you go through and it will be in growing order or in the order you instructed to put the things into. It also means that once you add the things, if you want to add or to remove a thing from a set, you can do, but it has a cost, an extra cost, because you need to put it in the right value, in the right place, okay? The standard doesn't say exactly how STD set has to be implemented, but normally it is a tree, okay? So it is made so that the insertion onto insertion and the results are of cost log n. So if you have n is n log n. Cost is of one insertion is order of logarithm of the size of elements in the set. Okay? Well, this I didn't say, so I will go back. No, that was here. What is the cost of accessing, let's say, to a vector? How much does it cost to go and let's say x1 or x22? If the size of the vector is n, then the cost is is, well, the cost of one axis is order of 1, and the cost of n axes will be of order n. Okay? So the cost is order of n for axis. Okay? Order 1, sorry, for one axis, and order n if you have n axes. You want to correct? What is the cost of pushing back? Which is what you was finding through yesterday. So you have an empty x, and you start putting back things.
And you said that he has to like copy.
Okay, so let's make the question better. I want to add the n elements into it. And you're telling is n. No, it's not n.
And
It would be n if the capacity was greater than n. But since the capacity is not greater than n, and the capacity will grow several times, then every time you have to copy.
It's 2n.
Is n to the number times the number of allocations. It's a large number.
Let me show the example. If we allocate chunks, to be precise. If you're lucky to be 12, it could be a Warsaw.
Okay, you're right. It is hard to give an estimation. Maybe what I'm telling is the cost will be the time to add the n plus the time of reallocations you have. Okay, and that time, every time you reallocate, apart for allocating, you also have to copy the things. Okay, so maybe okay, you're right. I should not estimate the cost, the complexity. But that's an expensive operation. Okay, that's what I wanted to. Matrix, well, the axis is order of the number of data, which is n by n, but I mean, just of the amount, the size 1 times size 2 for one axis, okay? I mean, the point, or when I say that it is order of log n, what I'm telling is it gets more costly if the size grows, not much. Logarithm of n grows low, but I mean it's not n, so it is lower than an axis to map. Order map. Okay, order map. So one thing, if you do std set x set x equal to 1, 2, 3. So you initialize with this, okay? Can you then do x 0? No, you cannot do that. You can look through it, but you cannot access one by one, okay? That's map. Map is similar to set, but it is different. So it is key value, okay? So you can do map 5 equal to Carlos. Okay. So you, in this case, you can put in a map, you could put a string if you like. This is simple, but you could also do map Carlos equal to 5. Okay. This is the, I think this is magic. Okay, magic. What it does, what the map does for you, is that it gives an identifier to this that is called a hashtag, well, a hash. It hashes this, and it converts into something that can be put here, okay? Every time you access, of course, the hashing is obvious if you have a number and an integer. It is not if you put a string, but you could have a vector. And then you would have to decide how that is hashed, okay? The map allows you to have an array with gaps. So, for example, I can have a map in which I have my x 0, 0 equal to 5, x 100 equal to 10, and there are just 0 and 100 in the map. Okay? If you access x of 1, which is not there, it allocates new memory. Okay? So there are ways not to allocate memory. Do not add memory. Just give me an error if it is not there. Okay? The map STD set is ordered. STD map as STD set is ordered. The cost is also, for any access, is also order of log n with a higher constant, of course. Okay? There is also a version with the same features, well, very same feature, in which you take out the keyword order. It is an order set, an order map. So asymptotic costs are the same, but it is cheaper. I mean, it just the constant is better to understand. If instead of set you write unordered underscore set or unordered underscore map, you will have another container which gives up the ordering. It still guarantees unicity and the same behavior as this, but without guaranteeing the order. And since you give up with the order, insertion and deletion are faster. Okay? The very last thing I want to do, going back to this, is sparse matrices that I saw that yesterday are, I mean, I think they were not familiar to some of you. Okay? So sparse matrix is a matrix in a sense that behaves as a map. Okay? Actually, you could, if you like, implement a sparse matrix in terms of a map. So, for example, you could use an order or a map on an order map such that Ij contains what you want. Okay? Well, it turns out that the reason for which we use maps, we use matrices, sparse matrices in our context, is to solve linear system of equations. Okay? In order to solve linear system of equation, normally you need that the product between that matrix and the vector is very fast. Okay? Well, the format of matrices that is used very, very often is not the unique one, but is the one that is king in our sector, let's say, is the CSR matrix. Compressed sparse row or row sparse. Okay, you can find both as CSR and CRS. Okay, but normally it's written as CSR. I just want to tell you how this is stored. Okay. Imagine that you have the data 1, 0, 10, 7, 1, no, 2, 12, just to say something. This is very small and there are few zeros. Okay, so it wouldn't make sense to use a sparse matrix for this. But the idea is that the things that are 0 will not be stored. Okay, so I will store just the entries that are there. Is it familiar this to you? Sorry, you are all familiar with this, because then I will not. No, you're not. Good. Then I just want to be sure I don't say. In the CSR matrix, you store 3 things, okay? Which is an array of values, an array of column indices, and an array of row indices. Okay? In the array of values, you store 1, 10, 7, 2, and 12. I mean, all the non-zero values that you have, okay? But not the zeros, you see? Then, the 1 is allocated in column 0. So I will say this is column 0. The 10 is allocated in column 2. The second is allocated in column 1. Okay?
10 column 3.
10, well, yeah, 0, 1, 2.
Okay.
1, 2, 3 if you were in Fortran. What I was telling. Okay, 2 is allocated in column 1 and 12 is allocated in column 2. Okay? And now what? Now the row indices tell me where the rows start. So the first row starts at 0 and finishes, well, no, not really. The second column, row starts, 1 and 10 are on the first, starts at 2. Okay, so what I'm telling is, essentially, those two values, when it is lesser than 2, when the index I use is lesser than 2, I have 1 and 10. Okay? Then 7, the second column starts at 2 and finishes, well, starts at 2. The third column is 0, 1, 2, 3. The second column starts at 3. Okay? So in here, my second column contains the number that are between 2 and 3. You understand what I mean? And, well, the third column, I mean, the next column is not there, but would be 0, 1, 2, 3, 4, 5. So what I have here is contained between 3 and 5, excluding 5. Okay?
I'm not getting it.
Yes. I'm just thinking to how to explain it better. The first two lines you do understand, right? Yes. So the third is an array that tells essentially where you will find every column. So imagine that I want to access, let me see if an example is clearer, okay? This is matrix A, I want to have A, 2, 1. So I want to access to the 2, okay? So I will look, I need to find where the data for 2 are, okay? So I look, I first go on the row indices. At the 2, I find 3, so I enter here, okay? So the data of the column, of the last column starts at 3, okay? So now I go onto here and I count 0, 1, 2, 3, okay? Now 2 and 12 are the data that are contained on the last column. Now I wanted the 1, I need to search between those, what is the, so which one is 1, okay? In particular, it's the first one in this case. So the value is 2. Is it a bit more clear or not? Try to imagine that I ask you A1, 2. What would you do? Just following the reasoning.
Let's go for the row.
So I go for the row, and what do I get from the row? 1. I enter here 0, 1. I get a 2. So the row I'm looking into starts at the position 1. So both the columns and the values start at the position 1 and the position 2 on those arrays. Okay? So 0, 1, 2. It starts from here, the column. It starts from this point here. And it will finish before 3. Indeed, I have just one number. Okay? So now I start looking into this value. In this case, there is just 1. And I'm asking for, well, it is not there. I should have asked you 1, 1. Right? 1, 2 was not there. Sorry. So now I start looking in this until I find 1. So this, the position that I have, it corresponds to 2, 1 is 7, which you have on the matrix. Is it a bit more clear or no? Yes? Now, when I was telling yesterday that the assembly has to do things, is because the first thing that you need to do when you assemble is that you need to construct at least this array and allocate zeros in that one, in one of values. Okay? But every time you want to add your Aij to your matrix, you're doing what I was describing, this sort of operation. Okay, and this will depend on the implementation. That's not a trivial thing. Now, the point is that if you try to do the multiplication of this by a vector, it is very, very comfortable to do and very, very efficient. It is all thought so that the past operation is matrix times a vector. Okay, this is used massively. In all finite code, you have something like this. Okay? And it is what I'm trying to tell is every time in the build you want to do a sum into a position, under the hood there is a search for where is stored that column. Okay? I just wanted to say this. That's a perfect hashing mechanism, by the way. That's no, not perfect. That's a hashing mechanism. Yeah, it's a perfect hashing mechanism because there are no gaps. It's a perfect hashing mechanism. This is correct. Okay, this is with this I finished, and I give the word to Charlie. Do you have questions about or the other data structures that you need or would like a comment on? No. So this I close. This you go, and no.
Chrome is bad. Just by book.
Well, please. My main hint is know how your containers work because you can have surprises. Okay, so the containers are designed to hide from you details of their implementation. They are comfortable to use normally, but you need to know how they work to understand what is the cost of things. Okay?
Can I ask you? Can you tell me what is an iterator?
Yes, it's a way of going through and not. For example, imagine that I have X, and X is a set. Okay? Now I want to go through all the non-zero members of the set. Then I will tell you, give me the first, then give me the second, then give me the third. That's a way of iterating through it. Okay? And you do x.begin plus plus, for example. Iterators can be random access if it allows you to do begin plus I skip, so give me the third at once. Or they can be how they called Random access or
No,
less
well,
than random access iterators?
Yeah, random access iterator and context iterator, but probably it's that.
What is, sorry?
So random access iterator, it tells you that you can iterate over regions of memory that are not contiguous. So imagine that you have a vector that for whatever reason doesn't fit in a chunk of memory that we're speaking before. Okay, you have to allocate half of the vector in a region of the heap and half of the other in another region. That's a random access vector. Okay, because when you reach the end of a chunk, you start with the beginning of the other. Okay. Non-random vector, non-random access iterator is something that it starts at some point and it ends at any other.
So random access iterator just allows you doing something like what you do for a vector. So x3, when you ask for x3, it doesn't go from 0 to 3. You just get the third directly. Right? That's what you can access at any point. Okay? With an iterator, on the other hand, you can only go through in a given order, a normal iterator without the random access. It has a definition. It is called something that I don't remember. I mean, the attribute is random access or
non-random access iterator.
no, I think it is another. I'm sure it's not random access.
Sequential.
I don't know.
It's plus and random iterators and not random iterators. I think. Well, forward iterators probably.
Forward iterator.
Yeah.
That's the. There are also backward iterator. So there are iterators that are not going in one direction. And every container in the STD, now the every maybe has asterisks, but that's a begin and an end. So you can go through the members. Okay. So for example, and this is the last thing, when you say for auto item in container, under the hood, if you use the iterator. But maybe I'm even wrong about this.
No,
but it's like that. So, yeah, okay. That's
Okay.
go ahead.
Am I? Okay. Well, so now let's change a little bit of topic, but not much, okay, because we are structures. And we wanted to tell you about more or less what are the such structures that we have worked in general in the world, and specifically what we have implemented in Kratos, okay? And this will be useful because probably what you will need to do, I mean, they will work with you. So you will need to find what is, for example, the element which is closer to another, which is the node that is closer to a given element, this kind of operations, okay? Which may seem trivial, but as you will see, they
Which cell is capped by your trimming curve?
for example.
You will need to do it very often.
Yes, I don't know how this works, so I will use the keyboard, okay? So no, all these this. So
That's
basically,
the screen.
touch screen. Okay. Okay. So basically, which is the main motivation on what all these methods came to be? So sadly, is getting okay. So 95% of the algorithms that I will show you here in the lecture that I will explain to you were motivated by getting. Okay. So if you want to do fast graphics, you need fast search algorithms. Okay. You need to know where all the things intersect and where they collide very fast. So we are not in the gaming industry. So basically, this translates that what we will use this for is, for example, embedding methods. Okay, so imagine that you have an STL of a city. This is the case of the city of Barcelona, and you want to embed it in a finite mesh volume. Okay. What you will need to do is to check where the STL puts our mesh. Okay, and for that, you will need to know which is the point or the element which is closer to a given surface or given vertex. I mean, you probably know more than I about this, okay? What you end up doing this is that you get a mesh, which, for example, this is the result of applying an OC3 to the STL of the Barcelona, and you see that we get here quality of a mesh, more or less, okay? Well, obviously, when you have the mesh, you can do simulations about it, okay? Another motivation for this is, for example, particles. This should be a video, but I didn't manage to get it work. In this case, what we need to know here is every time that these particles move through the mesh, where they are colliding. Okay, so in this particular case, if it were a video, you will see that the bigger particles get stuck in the first layer, the medium ones get stuck in the second layer, and all the remains go to the bins in here. Okay, so another application of searches. You need searches to know where these things are correlating to each other. Another particle motivation is this. This is a membrane, okay? And what you will see here is that when this chunk of falls fall into this membrane, it like oscillates a little bit, but everything stays together. Okay? So some examples of what can be used for. This I'm not sure. This example, do you remember which is this one? Because we answered me, but I.
Oh, this is something that explodes.
Yeah, so it explodes and it starts.
Yes.
Yeah, but I said, no, the videos, we answered me the presentation without the videos, so I ended up receiving.
Okay, no, this is,
Yeah.
I have this.
But okay, so maybe later we can show you the videos. It's
But this
very,
explodes.
it's very amazing, and it starts bouncing all over the place. Also, to know where they bouncing and which is the direction of the bounce, you need to know which element are you bouncing with. So you need a set for. Okay. Well, more examples. Probably this is I think that it's a bar that is pushing through that bar. We will try to find the videos later. Okay. So in order to do this search, we will need something which is called a spatial search. Okay. Our elements, our conditions, everything is in this page. So obviously we will need to look. Okay. So as an example, you might have this situation. Okay. You have an element, the blue dot that you want to search, and you have other elements of above. Okay. So there are several operations that you may be interested in. The first operation would be the searching radius. Okay. You will want to know which of the elements that are close to you, well, exactly which elements are close to the point that you're looking for. Okay. So you can pick like a threshold or like a given margin. Okay. So maybe you're interested in that. Probably you have a region which you know, okay, maybe I'm interested by that, but in general, you will want to know which elements are closer to you. The other operation that you might want to do is search an edge point. Okay, so imagine that you're trying to find an intersection. So to find an intersection point, you will have to find the point or the surface which is closer to the point that you're looking for. Okay, and lastly, you might need to know which are the key nearest points. For example, if you want to interpolate and you want the nearest points to you, you will need to make that operation. Okay, and this is a problem because if you look at this super 10 example, we'll have, I don't know, maybe 10 points. Okay, if you want to make this search, what you would do? Someone wants to try? So which is the strategy that you will follow to find these 3 points?
Don't answer. Point to who has to answer.
Okay, so for example, I don't know, Nicola, for example, that you are more or less familiar with this problem.
This is cheating subject. He knows the
The
answer.
easiest is to loop over all the points and compute the distance and check the mean.
Okay, so you will start for this one, look all the points, store the distances, and then select the minimum one. And imagine.
By the way, what is the cost of ordering something?
Well,
What is the cost of ordering?
what is the cost of ordering something?
Should have studied this in informatics.
And log n.
It's n log n.
If you do it well, it's an organ.
Otherwise, it's one square.
Exactly. So, and this is for
When,
1
so-
point.
If you want to use a data structure to store to index by distance, what would you use? Probably it would be a priority queue, this you cannot see.
Well, maybe.
Yeah, you can use a map or I use a map. How? Because
Well, you use the decimals at the
yeah, it's a priority queue if you were to.
But basically, the problem is that if you need to search it for a point, you need to search all the other elements, store the distances, order the distance, and then select the one. If you need to do it for another point, you need to repeat that operation. Okay, so it's n multiplied by n because you need to look for all the points multiplied by log of n. So you end up with a cost of n squared log n. Okay. For this example with 10 elements, this is fine. nothing happens. If you have 10 million elements, you die. So you cannot do it. So don't even try. Okay. So we need to find a solution which is more performant than, let's say, brute force. Okay. So everything against everything is called brute force. Never do that unless you have very few amount of points. Okay. Because I mean, you will not finish. So the main idea is here to divide and conquer. Okay, so we have to find the structures to store these, as we were using vectors before or matrices before. We need a special kind of structure to store the information of where these points are located in the space. So it's easier to make searches, and we will make easier to make searches, reducing the amount of, let's say, evaluations that we have to do. So the amount of distances that we need to calculate will be much lesser than if we want to do. Okay. There are like two kinds of structures that I will present you here, which are hierarchical structures and non-hierarchical structures. Okay, non-hierarchical structures, it's simply a way to divide the space in which every region of the space has the same importance as the other one. The example here is the bins. Okay, imagine the bins like a division of a space in cells, which every cell has a given position and a given size. You don't know anything else about it. And hierarchical data structures are things like trees, heaps, and this kind of structures, where you have a hierarchical order of the cells. Okay, in this case, I will present you first the KD tree. Okay, the KD tree is a structure that starts dividing the things in level. Okay, until you reach a level in which you have the amount of points that you selected. Okay, in this case, 1 or 2 points per region. You will see that this is divided irregularly. Okay, but it ends up having the amount of points that you wanted in every region. Okay. So the benefits and the cons of this structure is that basically hierarchical distributions are fit for any distribution, are very robust and effective, are very easy to implement. Okay, but they have a memory overhead. Okay, we'll see this later when I explain you the bins, but you need to be aware that hierarchical structures are not always fit for every kind of distribution of points in this space. Okay, non-hierarchical distributions, by the other hand, work for homogeneous distributions. Well, hierarchical, yeah, work for homogeneous distribution only. Otherwise, we will incur in super heavy overhead costs. Okay, the benefits are that super fast and very efficient, and the memory overhead it's only for the region in which you don't have anything.
What's the meaning of memory overhead?
Memory overhead is basically memory that you allocate that you don't know that you cannot allocate and you will use for nothing. Okay, we will see that later with example of some distributions. But for example, if I go back, okay, if I divide the space into this, okay, I will need to have a pointer for each region of those cells. Okay, but if you look at it, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells which holds nothing, and that's memory. So the information about those cells existing will need to be there for the algorithm to work. Okay, but it's memory that you're wasting. You need it for the structure to work, but it's not going to give you any advantage. Yes. So basically,
Sorry, are non-hierarchical, when are non-hierarchical approaches suitable? Like in what kind of homogeneous distributions in our cases, for example?
can you repeat this?
Like when are homogeneous distributions, for example, in our kind of like in mechanical problems desired?
Okay, I will tell you what are one distribution and the other distribution. At the end, we will see some benchmarks of like examples of distributions that you might find and how the algorithms behave better or worse in those situations. Okay. But an homogeneous distribution for use. So, for example, if you have something like, I don't know, a mesh which is perfectly, like it doesn't have to be a mesh like this, okay? This for me would be an homogeneous distribution, okay? Because your points are more or less so distributed like that in this space, okay? If you have something like this would be homogeneous distribution. A non-homogeneous distribution would be something like, so imagine that you have a point here, a cluster of points. Okay, then you have a super long distance and you have another cluster of points. Okay, but all of this is your model. This is a non-homogeneous distribution. Okay, so going back to the example before, if you want to make bits, for example, a structure here, you will start dividing your space like this. And you end up having like, I don't know, 25 cells or around 25 cells, which only 2 of them having information, okay? So when you end up more or less having the same problem. You have to make force here and brute force here.
So that's a big memory overhead.
Exactly. So it's a little memory overhead because you're wasting a lot of space. And also it's not suitable because what you're trying to do is to divide these points into the cells, but you end up having all the points into only 2 cells. So you will getting nothing. You want to say something, Pedro?
¿Cómo?
Ah, no, como tenía una levantada.
No, no estaba en mi mundo ahora.
Ok,
Está aquí mirando todos burocráticos.
no worry. So I will show you, for example, an example of how a KD3 works. Okay, so are you more or less familiar with what a KD3 is? Okay, so basically KD3 is a hierarchical special structure. Okay, and the trick here is that we are. So I will not tell you how the divisions are done. You can look that into internet because if we enter here making heuristics, we will not end until tomorrow. Okay, but basically the idea is that we are going to select the position in the space. Okay, so that we start dividing the points into halves. Okay, every time that we make something. If you want to do it as a tree from the top down, it will be something like this. Okay, so in the first layer, imagine that we have this. Okay, I will give names to the points so you can more or less track them. Okay, and what we are going to do is to make a first division. Okay, and we'll make the first division so that half of the points end in one side and half of the other points end in the other side. Okay, so in this example, I selected this here. I should have selected a line that partitions this by the other half. Okay, so the selection is done by something that is called heuristic. Okay, and if you select a better heuristic than the other, maybe the result is will be. Okay, this is like a wall of heuristics up there. And as I said, not the focus of this presentation. So the idea that you have to make is that when you make this division, half of the points will be in one side, half of the other points will be in the other side. Okay. In the next iteration, we are going to repeat this. Okay. And what's going to happen is that for each section, I'm going to do the same operation. Okay. In this case, I selected A in one side and all the others in the other. Why? Because I could trace a line here. Okay. And more or less, half of them were in one section and one were in the other. Okay. In the other side, I'm going to do the same thing. 2 points in one section, 2 points in the other section. Okay. Next level, I'm going to try to do the same. A, I did nothing because it was alone already. And in this section, I could like divide D, B, and C. Okay, so as you will see, I have another thing. And in the left side, in the right side, I could divide this perfectly. Okay, so I could do another level and redivide this. Yeah, probably I could. Okay, but not interesting. I decided that 2, more or less, it's okay. Okay, so what I ended up is that every point that I had before, it's isolated in one region. Okay, so now imagine that I want to make the operations that I showed you before. Okay, searching radius, for example. If I want to make a searching radius and I select a point which is, for example, here. Okay, I only could. Feel free. So if I want to make the search and imagine that I want to select a point that is around here, I will only make the search in all the areas that I calculated that are intersecting my search radius. Okay, so I had like, I think that I have this here. Okay, I have a division here, the other division here, another division here. Imagine that I want to search something that is in here, and my search radius is this. Okay, so I can, all of these can be ignored. Okay, so I'm reducing the search space from 8 points in this particular example to 4. Okay, so it's going to be at least twice as fine.
I have a question. I get the idea of the subdivisions, but how do you implement the computation? You know where to do the lines.
You will not have to do it because it's already implemented in Kratos. Okay, so I will make sure that you understand why we are doing this kind of thing. Okay, and which is better for which situation. But the problem with this is that I cannot tell you how to implement it or how to calculate this division because this is like another completely different problem. Okay. So in this particular example, you have this unknown, which is where to place the division. In the other example, you will not. Okay. But if you want to search for this, search for KDT division heuristics. Okay, so it will tell you, for example, in this case, I'm not sure, but maybe they'll do some kind of ordering about the coordinates and they divide using the binary representation of the nodes. For example, that could be a solution. But I mean, depending on which strategy you decide, you will end up with a K3 or another different. Okay, but the idea is that K3 tries to divide so that the maximum number of elements are the minimum number of elements are in the resulting sets. Okay. Another strategy, for example, the imply one which is very very widely used, is that instead of making the divisions like splitting the points, you select a point and make the division exactly there. Okay. So if you had like I don't know, you had like those points. Probably not this example, but the heuristic should be, okay, the first level is going to be putting this point, okay, then I'm going to be another which is putting this point, then I'm going to be another which is putting this point, something like that. Okay. In this particular case, it's much easier to implement because you know exactly where you have to put. So you select one point, so you select over the points, you select one, make the put. The problem is that if you want to make a search, you will need to select more areas, okay, because you know that the points are in the intersection of are in the points are like intersecting the division areas, and then normally the amount of sections that you have to search is 1 order of magnitude bigger than here. Okay, but I mean this is an implementation tool that you don't have to care about unless you want to implement a very big structure. Okay.
One question, maybe this goes in line with that, but how are like the subdivisions made here exactly?
In this
Like,
particular example,
if we are not taking like the
okay, in this particular example by hand. Okay, but for example, one way, if you are super interested, I can explain. Okay, so imagine that you have like the point A has coordinates, I don't know, 4, 5, point B has coordinates 6, 0, and point C has coordinates 4, 7. Okay, so what you could do, and I think I have a slide well, at the end, speaking about that, but basically you have to like index this. Okay, Ricardo was speaking about the hashing and how to make maps. Okay, so what you could do is to take the binary representation of that number. So for example, if you want 4, so it would be 1, 0, 0, and 5 would be 1, 0, 0, and you mix all together and you end up with a binary set. Okay, something like that. Okay, so that would be one representation. For B, the same. So you would do, I will put it directly, okay, and for B, you would do something like that. So we have something like that. Then what you could do is say, okay, the first division is going to be, for example, this byte. Okay, so all the numbers that have this byte at one position are going to be on one side, and all the others are going to be on the other side. Okay, if you do this right, you are going to force that half of them are in one position and half of them are in the other. Okay, so this line doesn't have to be exactly here, so it's not real. So it's not in that position in particular. It's just something that is dividing your elements at one side and the other side. Okay, if you start doing this, you will end having half of the elements on one side and half of the elements.
The idea is like we don't know the exact locations of the points. We just know that half of them will lie on one side and
exactly
on the other.
So this is like visually this is very clear, okay? But in the end, maybe A and F are in one division and E and D are in the other division. So the division don't have to make sense geometrically, say, but it's much more clear if I put it here, so you can. Okay. So at the end, you will have a representation of a number and the way they had stored. Yeah. Any other?
And for example, when you do the search in radius, you select a point in a certain subdivision, and you loop over the other subdivisions which intersect the radius.
Exactly. For example, then this is for searching radius. If you want to make the nearest one, you will need to have all the divisions that are like inserting the point that you have. Okay, because you are not sure which one is faster. Actually, Nicolo can tell you that in Kratos, particularly now we have a bug because this is a very complex operation to do in this kind of structure. So I mean, it's complicated. But we will see later which are the shortcuts. Okay. Now, similar to Academy 3, we have the octave. Okay. You remember yesterday, Manuel, that was speaking how to make the clipping of the meshes over the clipping spaces. He was using an octave. Okay. The idea is the same, but here we move away from the heuristics and odd ways to organize points, and we said, okay, we're going to divide a volume or a surface into 8 or 4 sections. Okay. So basically, if I don't know if I have. Yeah. So imagine that this is the example. Okay. So what we are going to do to divide. Okay. So we are going to make first division. Okay. We are going to have 1, 2, 3, 2 points. We can do another subdivision. Okay. So, but the divisions are always the same. Okay. So we're dividing the space, and here we will respect geometries. Here we are not doing both things about indexing, etc. We will start dividing it until we reach a point in which we are satisfied. I don't know if I put another level there. Yes. So in the example here now, we can see that in this cell we have 1 point, in this cell we have another point, another point, another point, another point, another point. Okay. Now, if you compare this with the beam dynamic, if you can see, since the distribution isn't homogeneous, we end up having cells which are not here. Okay. But there are less than in the other situation. Why? Because in here we are not like starting to subdivide more, because we know that in all this space we already have 1 point, so we don't need to go deeper. Okay. If we wanted to reduce it even more, what we can do is what I'm doing here. Okay, this is called like a shifted hood. Okay, and what we're doing here is instead of doing it in equal parts, we are respecting the structure of the octave, but we are shifting the size of the domain. Okay, so in this case, this particular domain is bigger because we're trying to fit all that we can the structures. Okay, we made a division, always respecting the structure, but sizing the cells as we wanted. So in here, as you can see, with one less division, we end up having the same number of cells, or the same, not the same number of cells, the same number of nodes per cell without having much cells empty. Okay, so the memory strain here is lower. Which is the benefit of this against the benefit of having less? Okay, so this is very good for traversal. Okay, if we are here, it's very easy to calculate for a given point which are the cells that are correlating with mine. In this case, it's good for memory because we're not wasting so much, but it's very bad for traversal. Okay, if we are in a point and we want to calculate which are the cells that are neighboring the searching point, we will need to make multi-complex operation. Okay, because it's not like, in fact, there's a implementation of this which the traversal time from one cell to the other is gone. So you don't have to calculate anything. You can just manipulate the bytes of the IDs of the cells and move from one to the other. Other restriction is that what happens if I want to make like more subdivisions in here. So probably that implies that I have to make more subdivisions in here because otherwise the it has like jumps of more than one level between one section and the other. Okay, that's also something that we want to avoid for efficiency. As I said, you don't need to care about all of this. It's already implemented, but you just need to know those are problems. It happened. Okay, so you need to be aware of which is the structure that will best adapt to the distribution that you have. Now, for the spatial sets that are not hierarchical, basically there is only one, which is called the beams. Okay, it's not for irregular distributions because it will lead you with many empty cells. Okay, but if you have more or less a homogeneous distribution, it's fantastic because it's very fast, it's super easy to implement and understand, and it's very memory efficient. Okay, so the idea is just divide the space into cells. Okay, you calculate the number of cells that you want, more or less. The heuristic is that you select a number of cells which is equal to the number of points, and you will end up having, if everything goes okay, 90% of the cells fill 1 point, 5% fill with more or less points, or one or more points, and some of them will end up empty. Okay, this is example. It's bad in purpose, so can show you that many of them in this particular example are empty, but you see the idea. Okay. Now, what you could do is to hybridize this. Okay, so you can make a data structure that more or less partitions well for a couple of levels, and then inside those levels, use another hierarchical or non-hierarchical structure. Okay, in this case, I'm showing you. Okay, I make a binary tree, for example, something that I did not spoke about, but you can do it. And in the third level, instead of going further, because, for example, I would have to divide more here and with a high number of empty cells, what I decide to do is that I put a list. Okay. You can mix it together. In Kratos, you can do it that as well. This basically it's the half of good of every wall. Okay, so you will have a solution which is good for every distribution. It will be good for catching the results. Okay, and you have a compromise between flexibility and efficiency. Okay, it will not be as efficient, for example, as an up tree, but it will be much less option. Now, how all this is implemented? Basically, what I was explaining to you is using hash tables. Okay. When we have to store this into memory, as I have explained to you, we have several data structures that are already in place in C++. Okay, and this is basically, in our case, vectors. You cannot do anything else. Okay. The main drawback of this is that, as I showed to you, there will be much precision. We'll end up with something that is okay. And try to reduce this, we'll have to use something which is more advanced, which probably will end up being okay. Now, in order to select which of the cells that I told you that have information are actually stored in our memory, we'll have to find a way to index them. Okay, and in order to do that, we'll have gaps. We don't want gaps, so we will need to have one function to tell us unequivocally where in the memory is every of the cells that I put. Probably not very clear, but if I put it to you with an example, you will see it easier. Okay, so imagine that we have our beams or our tree or whatever. Okay, we have all these cells. We imagine that it's like a matrix. Okay, and we have a point here, a point here, a point here, and a point here. Okay, so these are the cells that we want to store. What we are going to do? We could do it as a vector. Okay, so we could have a vector which has a number of cells equal to this and have pointers to every of the cells. Okay, so this will be 1, 2, 3, 4. Okay, and by this could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that would be 15. Okay, so that could be what you have 1, or imagine that you have 2 points. Okay, 1 and I don't know 8. So we will have this. In the position 2, we will have the cell which is storing the point number 2 in cell. For example, we have this and in this one.
So let's say in the vector you have the pointers to the other vectors.
Exactly.
Where you store the values.
Exactly. That would be a representation. Okay. This is something that we want to avoid because in this case, for example, this will be the overheating memory. Okay, which is something that we want to avoid. This also would be an overheating memory. All these will be an overheating memory. Okay. So ways to avoid that. Hashing. Okay. What we can do now. Basically, what is hashing? Is basically a way to assign a unique ID to every of the positions that we have. Okay, like, but maintaining some mathematical properties that are going to be useful. Okay, so in this particular example, basically what we want is to store the identifiers consecutive IDs. Okay, so ideally what we want is to reduce this to something like that. Okay, in which we have how we can do that. So in this particular example, it's super easy, okay, because it's two-dimensional, it's consecutive. So the only thing that the easiest thing that you can do is, okay, let's say this is index 0, this is index 3, 1, 2, 3. We have the 9th here and the 15th here. So I have one. Okay, so this is the easiest thing we can do. Okay, now imagine that we are in a 3D example, okay, and the cells are not organized. You cannot use this anymore, okay? Because we will end up having, for example, jumping from 0 to something that is behind and then something that is below. Then if you want to make a search, you cannot say, okay, search from here to here. it will be like you will have to go through all the vector, selecting every cell. Okay, this is efficient. So what we want is something that leaves in memory everything that we're going to set more or less together. So every time that we have to look for something, we don't have to go to another direction of memory to get. Way to do this, making use of functions. Okay, so in this particular example, in this vector, I'm assigning everything that is from this position to this position to the position 1, from 150 to this position to the other, etc., etc. You can look more in the table PDF, so it's not more. But basically, an example would be, okay, if our keys are, for example, names, as Kratos was showing to you, basically what we're going to do is to pass it through a hash function, and that hash function is going to assign it to a position of the hash. Okay. Now this is used for associative arrays. Okay, associative arrays are exactly this example. String cells. Okay, so you're going to make a cell over a string. We would use that. Database indexing for the same thing. Okay. Sets, as I will tell to you, one way of implementing sets is using the heap. Another way to implement sets is making this to reduce the memory space that you need. Unique data representation, you can forget about that, and spatial searches, which is what we are doing. Okay, so a little example of how this would work. Okay, so in this case, imagine that we have those numbers. Okay, and we select that our hash function is just to adapt the coordinates. Okay, so for the first one, we'll add the coordinates and it gives 2, no problem, we store it there. For the second one, we sum up the coordinates, it gives 6, no problem, and we will happen for the third one. 2. And we have a collision. Okay. So this is the main problem of the hashes. When Ricardo was speaking about perfect hashing or not perfect hashing, was speaking about this. Okay, how we select a function or how we modify the hashing so that we can ensure that only one position or only one element is going to end up going to one position. The sad news is that it's a little bit impossible. Okay, so we need to find a strategy to deal with this situation. For example, open everything. Okay, if it doesn't fit in the first position, put it in the second. So there are a number of strategies that you can use to deal with these situations. Okay, in particular in Kratos we have perfect hashes, so don't worry about that. But basically, separating chains. Okay, that's what I tell to you before. You can do it. Okay, if instead of hash you have an extraction inside that hash that sort the elements that are inside, you will reduce the chances that are collisions there. So imagine in this example before, if we have a set here and those elements are different, we will end up having a hash which contains a set. Okay, so you're introducing the overhead of using a set, but here. Another solution that you can use with this, use more complex hashing strategies. For example, Google hashing. Google hashing, instead of having one hashing table, it has 2. If it doesn't fit in the first one, it will fit in the second one. Okay, and it will do it in a way insights that first we will try to put it in the first hashing. If it doesn't fit there, it will take that element. We calculate the hash for the second one and put the first in the first place. Okay. If it doesn't fit in the second, or we find a collision in the second hashing table, what it's going to do is to calculate the hashing for the first one, and it's going to repeat this process. Okay, causing that the element that was pushing the first one to the second hashing table, it's pushed to another different position in the second hashing table, so you avoid that collision as well. Maybe they can put an example. I mean,
doesn't it have a big overhead?
It has an overhead, but it only has an overhead when you create it. Okay. And more or less, the overhead of all these search structures is so the idea is that you move the overhead from the search itself to the creation of the structure. So the creation of the structure, we are very lenient on that, like take more time or take overheads. Okay. If the search, then it's going to be super fast. Okay. So because the constructor, we are going to do it typically once. The search is going to be repeated multiple times. Okay. So we want to reduce the cost of the thing that is going to be repeated multiple times. But yes, I mean, all of these structures have overhead. But typically, the overhead that you're going to pay using any of these strategies is much lower than the overhead that you will have like doing searches by brute force, as you will see if you select the proper story. Okay. Actually, you can discard collisions, no, in this case, but anything. Now, lastly, about the ordering methods, okay, I was speaking to you about the indexing representation, which is basically these two things, okay? So you have to think that at the end, what you're doing is manipulating the computer memory, okay? And the computer memory has some strict rules of how it's organized, okay? You more or less, do you know how memory levels work in a computer? Cache, levels of cache, how to move data, more or less. Okay, so super quick explanation. Okay. So basically, in a computer, you have like several levels of memory. Okay, so you have RAM, right? You will have L1 cache, L2 cache, until L cache. Okay, typically this is on 3 levels. Okay, but it will depend on the machine. Okay, what happens is that if we go in this direction, we increase in size. And if we go in this direction, we increase in speed. Okay. Problem. If we have a lot of space, we have very few lectures speeds. If we have a lot of speed, we have very few sizes. Okay. What we try to do is to fit. And yeah, so and this works in something we call pages. Okay. So for example, if you have a RAM here, okay, it will have several pages of memory. Let's say, well, imagine that this is a page, okay. If we move to the L1 level, okay, a section of this will be moved here all together, okay. So this will continue, okay. So this represents here, and we will have another level, okay. So what happens when you access the data in a computer? Okay, so imagine that our vector it's stored, for example, in here, okay. So you will have, this is your initial position, and this is your final position. And say, okay, I want the data which is in the position N, which is in here, okay? The computer is going to say, okay, I'm going to bring all this memory to this level of cache, okay? And we are going to repeat the operation. We're going to see that the data that we need is here, and we're going to bring all this position of memory to another level of cache. And probably I'm going to do one because 3. It's more than, okay. I'm going to repeat this. The position is here, okay. I leave it here. What is going to happen the next time that I want something from that particular position of the vector? So imagine that this is I want n. This happens. I want n plus 1. It's going to go here? No. It's going to go here? No. It's going to go here because it will detect that the information is already in this position of memory. Okay. Now, it will not have to pay the cost of indexing this memory. It will not have to pay the cost of indexing this memory. It will only have to pay the price of selecting the position of memory in this particular level of cache. Okay. So, for more or less you to understand, every time that we do a level of cache is an order of magnitude faster. Okay. So if it takes 1 unit of time to access memory here, it takes 10 units of time to access memory here, and it can take from the order of 100, 1000 orders of time, more time to access that. We're speaking about milliseconds and nanoseconds, but still the difference is enormous. Okay, so if you're iterating over a vector and you're taking chunks of memory together, okay, you're going to make much more of these kind of accesses than those here. Okay, now why this is important and why the ordering of this? Okay, because for example, imagine that you are trying to search like you have point here. Okay, this is the normal ordering. Okay, 1, 2, 3, 4, 5, 6, 7. So a regular order. You try to find neighbors of these sections in here. Okay, so if you are here and you want to search neighbors in those 4 cells, okay, you're going to bring for memory probably this cell, this cell, this cell, and this cell. You're going to pay one time the big access, one other time the middle access, and one time the slow access, okay? But when you will try in this cell, you're going to repeat, you're going not to pay the big price, but you're going to pay the small one. But if you move here down, okay, so imagine if our page can hold 4 positions only. So if in here we can only store, or we can only bring 4 cells, it's going to bring the cells from here to here, because this is the order, okay? So you're going to pay slow, fast, slow, again, because you have to bring all this line, fast, okay? This is bad. If we use that ordering, okay, so if instead of using the normal 1, 2, 3, 4, 5 positions, we end up with a Morton ordering, which is the one that I showed you there, okay, we'll have a small price, big price here, small, small, small. So the algorithm is quite faster, okay? In this particular order, the cost is going to be also fast, okay? But this has a property that it's iterated a little bit different, okay? So for example, maybe if you are searching in an elongated search radius, this is better. If you are going to search in a more vertical pattern, this would be better, okay? So it's important that when you're indexing and you're choosing your hashing function, you select something that is ordering this space in a way that is suitable for you, okay? And because of that. And basically here there are 3 examples, which is row-based, the normal one that you know, Morton, which basically is interpolating the bits of the coordinates, so interleaving. If you have also Morton would be, so if you have a coordinate which is in 4, 6, and this is 1, 0, 0, 0, 1, 0, 1, 0, a Morton ordering would take 1, this one, then this, then this, then this, then this, then this, and the other one, and we create this hashing, okay? For example, this is one technique. Piano Hilbert, it more or less does the same, but it does it in a different fashion. I don't know if they like group them together, okay? But there are a lot of strategies. Like
in Kratos, we use a special search algorithm. You have to select which other image you want to use.
We select it for you. Because most of the time, what happens is that every one of these ordinations is suitable for one structure in particular, okay? But you need to be aware that this could happen, okay? If you want to implement a structure by yourself, because none of the ones in Kratos is useful for you, you will have to take this into account, okay? Otherwise, maybe if you are working with 1,000 elements, 1 million elements, you will not notice the difference, okay? But if you start escalating this, it will be important. We are speaking about maybe 10 times faster. Okay. Now, well, for consideration, what I was telling to you, bootstrap functions will reduce the access time of things, basically because of Takeche. Okay. Hash will depend on the input. Okay. So there are some generic hashing functions, and I mean, you don't have to worry about this because it's in Kratos. But normally, if you want to implement a hashing function, you will have to take into account all the space of things that you want to hash. Okay, because maybe it works for a subset, but it doesn't work for a full set of data. So take this into consideration. Well, try to distribute the data uniformly, obviously. Generate different values for similar keys. This is also important. So normally, what you would want is 2 things to be equally sparse in the hashing table. Okay, so you don't have gaps in between. Well, more or less, is what I've been explaining to you as well. Now, problems you may find. You may not have the whole set of things that you want to hash at runtime. This at the compiling time, this is something that can happen, so we'll have to adapt. Maybe it's not possible to do everything that I explained to you perfectly, so you will have problems. Need to support dynamic resizing. We will need to change the things that we are indexing in the runtime. This is also something that you may have to consider. And if we can insert or delete elements in so when I was speaking about how to deal with collisions, for example, this is important because if we make a perfect cache of some data and then we start inserting things that were not thought for that, it's going to crash. So take this into account. Now, important topic, parallelization. Okay, so probably this was not as important some decades before, but now it's like primordial. If you don't parallelize the structures, you are going nowhere. Okay, so it's important either you will have to do it with OpenMP or NPI, but you will have to prioritize. Okay. Because basically all our computers now, so the architecture of the CPU is multi-core. If you don't exploit that, it's going to be slow, but much slower. Okay. There are three mechanisms in which you will be able to exploit this, and I say we that already it's implemented in Kratos, but not as good as the other thing. So probably it will require more from you in this path. Okay. OpenMP, which is single memory parallelism, super easy, nothing happens. You have one memory and you decide from which part of that memory one processor acts and from which part of memory to the other processor acts. If you use perfect caches, which we do, it avoids collision and critical sections, so something that you don't have to worry about that as well. And in general, it's super easy to implement. So you don't have to take things into account. There are specific functions in Kratos. Maybe Ruben will tell you about this later. We have block for eaches that can iterate over all these structures. I mean, super easy to implement. MPI programs. MPI is, anybody know? Yes. No. So basically, this is distributed parallelism. Okay. What means distributed parallelism? That you don't have in access to the memory where the data you want to iterate on is. Okay. So imagine that I have a search structure and half of the elements are not in my computer or are not in the program that I'm running. Okay. So I have to ask specifically to the other program, okay, give me this data to outcover it. Okay. It has partitioning problems that need to be considered, and we show you an example, okay, and there are different approaches for dealing with it. Finally, you have GPU, it's extremely fast if you manage to implement, okay? Well, if you do it, please tell me, and we will include it into Kratos. We haven't been able to do it in 20 years, so feel free, okay? Now, what I was mentioning about parallelization and the problems that it might include is that if we have to make parallelization, we have to hierarchically divide the computation that we want to make. Okay, so imagine that you want to search the points that are close to this setting here. Okay, each one of the gray colored cells will represent a domain of memory. Okay, and will represent the world which one CPU is going to do. Okay, now this CPU is only going to see this region here. Well, you have here probably easier. Okay, the CPU is going only to see this region in memory. Okay, so if I have like, well, if I divide my space for process 1, process 2, process 3, and process 4, my point is here, and I want to make a search in radius. Okay, what is going to happen is that this process will have to make the search for here, and it doesn't know about what's happening here. This process will have to make the search for here, and it's not knowing what's happening in the other places. Same for this other two. Okay, so we will need another step when we finish this to get, okay, get the results from process 1, from process 2, from process 3, from process 4. Okay, get it together, and from the partial results, get the total result. Okay, for MPI, as I tell you, very easy. I need to do something. For MPI, what is going to happen is that since I don't have the results in, so I don't know what's happening here, what's happening here, I will have to ask every processor which of the results. I will have to decide which processor calculates which is the final result, and I will have to communicate to the other processors which has been this final result.
You have to wait until all processors are done to ask.
Exactly. And you don't know when the others have finished, so you need a synchronization point. So this is very important. Okay. I prepare an example to show you that. So for MPI, I mean, it's done more or less automatically, so you don't have to worry about this. For MPI, you will need this. Okay. As I was saying, for example, this is an example of what's happening if I want to search all the elements that are in a radius. Okay, so search the neighbors using the structure of bins. Okay. Now every process will have a local set of information in which it can calculate those neighbors things. Okay. Now all process will share a common part of the data, which is called the interface. Okay. So let's say there is no, also more than there is not, there are parts of the data that are shared between processors, and we need to do that in order to communicate results, okay, and to know where we are partitioning things. In Kratos, we will use something which is called global pointer, which more or less hides this division and lets you act with the data as if you own it where you are not. Okay, and the search then, of course, is executed in chunks which belong to every processor. Okay, so super easy example. Okay, every square, okay, belongs to one processor, which is very similar to what I did there. Okay, so as you can see here, every processor, of course, has its own set of cells. Okay, and some of them are shared with the processor. So it not means that it belongs to both of them, but it means that both of them have calculated the same cell. This is something that we can have. Okay, now what we're going to do is first we're going to search the neighbor of the processor in which I am. Okay, no problems there. Then what I'm going to do is to say, okay, which processors are intersecting the area in which I might find neighbors. Okay, and in this case, you will see that there is another processor which is overlapping the searching area of my element. Okay. Then what I'm going to do is, okay, I'm going to transfer the object there. I'm going to repeat the same operation. Okay, having this object here, even if I have not the mesh in there, because I know that the possible result could be there. And then I'm going to communicate the results. Okay. I mean, again, this is something that in Kratos is already done. I later probably give you through the code, which is in the search example, but bear in mind that this is something that will happen underneath. Okay, so it has a cost. Now, speaking about distributions, how they are organized that you were asking me for, this is basically what we understand by the uniform distribution. Okay, so you have a domain, the domain is full. In here is a structure, but it could be unstructured. Okay, so could have a cloud of points. Okay. Another distribution that you may have, like basically what I was showing you there, which are cluster of points. Okay. So basically, this is something that could happen to you as well. You have one concentration of points, another concentration of points, or chunks of points, which are distributed in the space, but there is a lot of distance between those. Okay. And also this uniformly distributed clusters. That's another representation. It's something that can happen. Okay. Point distributions where all the things are, or there is a section in the model with a lot of concentration, with other distribution of the model, very low concentration. And finally, you can have also a line distribution, okay, which is something which is very local, but expands in a very big chunk of space. So basically, just to show you a little bit what are the benchmarking on why it's important to have all of this in consideration. Okay, this is more or less the general view. Okay, every of the sections is one of the distributions that I showed you. Okay, and the columns are the effect of using every edge of the structures that I presented to you. So, for example, in line, if you're static, well, static of dynamic means I didn't show to you, but the static means is something in which we never change the allocation of memory. Dynamics is something in which we normally move the allocation of memory. Okay, so as you can see, for example, in the case of the line and in the case of the beams, you imagine a 3D beams of the space. The only thing that is going to be filled is like if you had a diagonal matrix, it's the diagonal in which you have your line. Okay, so 90% of the cells are going to be empty. When you make searches over there, obviously the time is huge. Okay, for example, for a cube, we'll see that the smallest time is the static means. Why? Because we have allocated once. It is true that for some of the cells, we're going to have a lot of points in the part where the more points are allocated, but in the others, we'll spend a little bit of memory, but since it's static, we don't care. Okay, so the time is going to be lesser. So we'll go through some of the results. For the nearest point, it's much worse. Okay, in the case of the offset cube, for example. Why? Because since we are searching for the nearest point, what can happen is that for example, if my point is here and my cluster of points are here, and I have all these of cells here, what I will have to do is to say, okay, which is the closest cell that is from the searching point? This cell, it's empty. So I have to expand my search. This is going to be my new search. Then this is going to be my new search. Then this is going to be my new search. Okay, so you see the problem here with this structure. as the number of cells empty are huge, I will have to perform an iteration over all the cells until I arrive to the one that has results. So it can give me a result. So this is why you're seeing this super high numbers here. Okay.
In that case, which is the most preferable subdivision algorithm?
In this particular case, I would say the static beans or the KD. Okay, because all these, so if we're in this case in particular, all these KD3s, we have KD3 average, which is how we will calculate the line, okay? But as you can see, OC3, it's bad because, again, we end up with a lot of empty cells. In this particular case, KD3, it's super super good because if we think a distribution which will have like 3 points in here, and this is your searching point, probably, and this is our domain, okay, the KD3, when it was created, would have done, okay, first partition here, second partition here, another partition here, another partition here. If I'm in this, my neighboring cells are directly this one. So I skip all the cells that are in between, because in this particular case, this cell is huge, and I know that my neighbor probably is the one that contains the elements.
KD3, you try to put just one element, one node per element.
If you can, you try, but it's not always possible. So that's the trade-off. So probably in this case, for example, if you look at it, we have K3 average, K3 middle point. Okay, so that's some of the topologies that I showed you. K3 middle point is the one that is implemented this. The average is the one that more or less calculates the centroid of the points and then baseline that. And the other one I don't remember because I didn't implement it myself, but it's something like that. But I mean, the general idea is that K3 in this case is much faster than any of the static dynamics or OC3 or whatever, okay? Because the number of cells is lesser. Okay. Well, more examples in this case, for example, cluster cube, the same generic cube. In the generic cube, for example, you see that the dynamic and the static beams are much faster than any other three. Why? Because the data structure is faster and we are in a distribution which distributes homogeneously over the space. So that's the perfect line splitting of the space. So that's why we have these results. Okay. And this is for paralleling. So as you can, this is more or less for you to see that if it's implemented correctly, it escalates well. Okay. So in here we have the time that it is one processor, two processors, four processors. Okay. The important is not that. So the important is not that that the time is high, but that you can see that the reducing of time when we double the number of processors is logarithmic. Okay, so if we double the number of processors, we are splitting into the time it takes to search. Okay, and this is because it's more or less well implemented. It could have problems, for example, here. So not so good, but so you are fine over, but it should more or less work linearly. Okay. Same thing. And well, that's the same. This is because it was parallel also. I have a lot of that. Yeah, and you here more or less you can see it better. This line shows you more or less which is the scalability in Kratos, searches for example that we have with 10 million elements more or less. And as you can see, the generation of the beans scale more or less up to 24 processors, okay, which is more or less good. The search also scales more or less up to 48 processors, and you have the line for the idea for reference. Okay, if we could increase the number of processors, probably it will flatten up. Okay, so there is a point in which the overhead that you're paying for parallelizing and making all this distribution, it's so high that it not compensates for the gaining that you are selling. Of course, the overhead that you buy to make this so to parallelize this structure, it grows with the number of processors that you're including. Okay, because actually the data structures that you need to keep track of the number of partitions, where to send everything, and calculate these kind of things, it grows with the number of processors. Okay. In this case, for example, we had a weak scalability. Weak scalability is like a trick because we are, instead of like reducing the number of processors and reducing the time, we see what happens if we double the number of elements and double the number of resources that we have available. In general, the more number of elements that you have in a problem, the better it will scale. Okay, so if we double it, we more or less hitting the overhead because we're increasing. So as you can see, in this case, we were scaling up to 1,500,000 cores, okay, which is pretty good. Realistically, today, you should not expect to scale more than 6,000 cores. Okay, that would say it is a hard limit in Kratos, but if you reach that, perfect. And basically, in here, you see the impact of the chunk size. Okay, chunk size is well, the number is chunk size. Probably this is not the best graphic because this should be inverted, but chunk size is the number of elements that we have at the end in the one graph. Okay, so the more elements we have in one side, for example, here, it is lower. If we have a larger number of chunk size, so less elements per chunk size, the search is much faster. So that's the only thing. So basically, this is all for the searching algorithms. Probably you have a lot of questions, so feel free to ask. So in Kratos, all of this is located in search structures. Okay. So you go to Kratos search structures, you will have all the algorithms implemented in that, ready to use. Okay, so I think there should be a break now. I'm not sure because Ricardo is the one that controls this, but yeah, well, it should have been half an hour ago, but you're free to go. And when we come back, I will show you a little bit the structure and organization of the repository, how you can like request access, make pull requests, these kind of things. And if you want, a little bit of organization of how to run simulations, Kratos, where are the steps, etc. And then Ruben will come and you will make the hands-on of Kratos. Okay?
Thanks a lot.
Starting should take a break.
It's not like a break. It's a real good idea of my time.
Ah, yeah.
Because I never speak. Okay, thanks.
Yeah, because I'm not having. The previous one was. Wow, actually it's really, it's intense, but it's very, very interesting these days. It's very well constructed. Which you can very basic.
And guess what they want? At least if you need anything, it's funny. CRA supervisors, so.
Todo menos que tenéis que firmar. No has firmado y. No. Señor.
Sí, claro. Tú eres una chica.
Ricky.
No, Kratos.
Bologna lost yesterday
Very bad,
4-1.
very bad. And
4-1.
I mean, basketball is not football.
What?
It was basketball. Yeah.
So it was another because I heard in the bus that who won yesterday?
No,
4-1.
yeah, it was also playing the football.
How much?
The basketball team, the Barcelona won by like 30 points. I think I have updated something, and now it's saying.
Okay, because maybe you have a.
Yeah, but I try to.
No.
The other
it's fine.
This guy. 14.
Maybe it has rotated to 16. Ah, you know. Why? No, copiado.
Con comando.
Sí, ¿cómo hace?
Sí. Y como ves.
Beauty is not there. La 17.
17 así.
¿Por qué coman? ¿Por qué coman? Es que no entiendo.
No,
¿verdad,
ahora me voy a hacer así.
Y no funciona muy bien. ¿Cómo se llama?
Se llama. No, se llama
Arteros.
Ah, vale. Ah, claro, eso es bastante interesante.
Sí, pues.
Tenemos un tubo que se llama Llama.
Y si funciona eso, ayer estaba aquí, como tengo dos casos compilados, y aquí quería, en otro quería utilizar ese Kratos.
Vale. Esto tienes que poner el.
Sí, 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 claro. Tú una vez, lo sé cómo se llama en Linux, en Mac, ¿no? Lo has hecho en, pues, como la bash de Mac. Así que,
Vale, esta es la variable. Entonces tienes que cambiar las variables que le ponen, de ahí el D, la variable. Vale. Entonces, esto está,
ahora es,
creo que está en home profile,
¿vale?
creo. Pero a ver, en principio no lo toques, ¿eh?
Sí.
Vale, sí. Sí, es aquí que tienes. Ah, vale, pues sí, aquí te pasa.
Aquí también hay, ¿vale? Y hay,
Claro,
hay Kratos.
Vale, entonces, para cuando quieras hacerlo, te copias las de aquí.
Y simplemente,
Haces export.
sí, y en vez de Kratos,
Sí, pero
Pero
quítale,
poner-
o sea, quítale este cuando directamente ahí DLD library path, directamente home Kratos release sin esto, el principio.
sí,
O sea, quita esto.
quito esto.
Sí, cuando
Porque eso es,
esto es que coja lo que tienes antes y le añada cosas, ¿vale? Entonces,
Vale.
si ya tienes puesto esto de aquí, te va a coger primero este y después te va a coger el que le pongas. Vale, entonces no te va a funcionar.
sí,
Pero si lo pones a más uno y esto.
vale. Entonces, lo mismo,
Sí.
sin,
Para Python Pad lo mismo. Coges y quitas todas las Python Pad del principio y pones directamente Python Pad, eso es, por Python Pad igual, con Kratos,
vale.
y ya está. Si quieres, métetelo en un script, que sea que ponga use Kratos, que te haga shows.
Vale.
O sea, el comando shows básicamente sí que ejecuta lo que tiene dentro en el terminal del destino.
Perfecto. Gracias.
¿Sabe? Sí. Está hablando ahora con su tienen que organizar pues, un curso y la gente de ellos nos interesa mucho. A pedido si lo puedes compartir lo que usaste por dentares, estas
Eso
presentaciones.
sí, eso es compartir.
Se la compartes y lo que le he dicho es que el objetivo es que al final, que si la mejora y tal, perfecto, que luego vayan a la documentación.
Sí, a ver, a mí me gustaría preparar porque teníamos prisa, no me tengo que preparármelas, pero si las queremos poner en plan cursos, yo lo pondría más con más ejemplo y dónde está en Kratos.
Pero es que
mucho es que esto dónde está en Kratos, explicado, que dárselo. Pero, o sea, digamos, está muy bien en plan teórico lo que tenemos, pero si lo queremos organizar como un
hasta
curso,
lo podemos registrar bien, eventualmente grabar, quiero decir.
sí, o sea, de hacerlo con. Vale, sí,
pero
que
eso de
falta-
compartírsela y que él también ponga
Sí,
material, te puedes sincronizar con.
Vale, espérate que.
Sí, no tiene que ser algo, pero que. ¿vale? Otra cosa, eventualmente, cuando es que vendrían los dentares o irías
A ver, yo tengo que mirar a Nino, porque he dicho que hablaría con el chico este ruso y habla con él. Entonces, ahora me tengo que preguntar a ver exactamente qué necesito hacer para que se acabe el proceso, que cuando lo tengas se lo envío a pero la idea es que mañana ya le envíe el mail.
Pero más si eventualmente me dices una que vendría muy bien, porque consideramos bastante importante también que era gente de bus, de la SER, de y podrían,
You are the worst. You think you can work.
Vale, sí,
Sí,
es que-
quería
I'm looking for.
Realmente hubiese querido.
Yeah, that was before, but that's because it was open. Ah,
No sé, igual no
¿sabes? Autosado, que si tú te quedas en una posición, es que me preguntes. O sea, si no,
Pero es que también tienes una vida, es que decir, no es. Yo, por ejemplo, yo lo mío, viajar a mí supone un problema. Vale, perfecto, lo veo esto.
I should find it in Instagram.
Vamos un foro para ver si hago datos que no están, ¿no? Lo que aprendes, ¿no? Pero sí puedo resumir.
No sé.
Maybe. I will search for 5 minutes.
When do we start?
Good question. When you want.
Right.
5 minutes. 5 minutes.
Okay.
The session is going to be much more light, so.
Vale, vale. ¿De dónde eres? Carlos, tío.
Sí, de aquí. Vale. Pues. Charlie.
No, Charlie, que con Charlie.
Sorry, but cuando vienen todos de plan, no, Charlie.
Claro.
Yeah, I didn't know your true name until, I don't know, 1 month ago. Yeah. That still happened.
¿Y qué estudiaste?
Yo informática.
Ah,
Yo de métodos numéricos no tengo ni idea.
ya.
Informática sí.
Y estudiaste aquí en la UPC, ¿no?
Sí, aquí aquí al lado.
Y o sea, ¿qué estás haciendo el puesto con el doctorado?
No, estoy haciendo doctorado.
Con Ricardo.
Sí,
Bueno, con.
un poco con varias gente. Pero sí. A ver si acaba de nada.
¿Cuánto llevas?
No sé, 4 5 años ya.
Yo bastante, ¿eh?
Sí, claro, porque, a ver, es que tuve un problema, porque yo empecé con cosas de estas de malas y tal, pero salieron los franceses, como siempre, y
Sí.
hicieron lo que yo iba a presentar, entonces tuvimos que cambiar de tema.
¿De verdad?
Sí, y ahora estoy haciendo cosas de inteligencia artificial y cosas de estas.
O sea, que publicaron en una universidad como el trabajo que tú estabas haciendo.
No, pero, o sea, justamente su equipo de investigación estaba haciendo lo mismo que permitimos hacer nosotros, que lo acabamos
Ya.
más fuerte. Así que nada, tenemos que trabajar 2 años, entonces volví a empezar hace 2 años y ahora pues, después pilló el COVID, bueno.
Ya, qué
Algo
horror,
problemas, mi supervisor se fue a trabajar en una empresa y luego,
Dios.
todo problema en el doctorado. Es una cosa.
Ya. Pero ¿te quedarás aquí, crees? O no?
A ver si me dejan, sí.
O sea, digo, en Barcelona o la UPC.
Sí, yo sí.
O sea, tú querrías quedarte aquí, ¿vale?
Sí.
Qué bien.
Claro, tengo la vida montada aquí. A ver si me tengo que ir viniendo.
Ya.
¿Tú quieres aquí también?
No, yo de Gijón.
Bueno, pero.
O sea, claro, o sea, digo que sí, soy obviamente aquí, pero en plan me refiero que sí soy de Gijón. Y estoy allí y pues pasa con estoy en Pablo.
Vale, esto fue ahí.
Sí.
¿Pero que también el doctorado ya o perdón?
¿Cómo? No, estaba empezando el mundo. Hace 2 meses.
Ya verás que divertido.
Ah,
Verás que divertido.
ya, bueno, veremos a ver qué pasa.
Sí, vale, una cosa que cada yo también tuve esta aquí. For now, the one missing the pizza because otherwise I do have time to keep it, okay? Well, now super light session, okay? So this will be about Kratos organization, how the repository works, the resources we have there, how to need to make pull requests, things like that, okay? So this is more or less for you to start with Kratos. Some of you have already compiled it and start using it, okay? But I'm going to show you more or less an overview of the project, when it started, etc., etc. Okay. So first thing, who we are, okay? So basically, this is us, the team. This is taken from the other terras, okay? So this is taken from another presentation, so probably the translation doesn't make sense isolated, but basically the Kratos team started like with Jan and Ricardo 15 years ago, 15 years ago, more or less. It started to grow in people from team, and it ended up with the team we are right now, which is all the people that you see here, plus new incorporations, okay? Nowadays, we are present in the industry and academia, okay? Some of the more relevant places we are, we have Kratos is the University of Thun, Altair, Airbus, Deltare, Siemens, Sonera, we have also with Antonio in the University of Padova, okay? But the idea here is that this started as an academical project, but it grew to be something which the industry is already used, okay? So the idea here is that if you end your PhD or whatever, you go to the industry, it may happen that you find that they are using Kratos. No? That was an utopia some years ago, but it's now a reality. We are very proud of it. Okay, so there are other companies that we know they are using Kratos, but they don't want to tell us. So I didn't put them here. Well, I will not say it. Now, basically, as any other project, okay, this started as something very small, okay, but it grew, and with the growth of the project, a lot of problems arise, okay. So basically, we have to think that from two people that were sharing a code with a USB, we passed to a code that is used by more than 100 people already. All of them pushing code at the same time, wanted things to work, anything can crash, etc., etc. Communication was very difficult because everything was isolated in its own environment. So as you will see later when I show you the structure of how Kratos is organized in application and that, you will see that for every group of people, they have their own application and they can live in their own ecosystem, but also there are parts that are shared between all of us that need to be done, but then, well, problems, okay, happen. Also, we have a lot of problems because we didn't, at some point, we didn't have a stable version. This is very important when we develop a code, okay, that have something that is working regardless of the changes that you're doing, okay. We also had a problem with the platform and the different kind of users that we have who have used it that wanted to use Kratos in cluster or servers. We have students that have the laptop with more or less capacity or CPU power. As you can see now, we have users with Linux, Windows, Mac, for example, which is not supported very well yet, but we're working on it. Sorry. Also, we have a lot of internal processes, okay? So you, as academic users, would want to modify the source code of Kratos, but for example, a user from the industry would not care about that. They only want simulation or results to most parts. So we needed to compile releases, structure the code, provide benchmark examples for people to trust in the work we are doing, okay? And this is something that we didn't have at some time, okay? So we identified the list of problems that I can go with. They are not many interested. And we tried in those recent years to guide Kratos to a position in which all the problems that we are seeing here are more or less solved, okay? So basically, I just wanted to show you. Why do you use it, for example, GitHub? Okay, so I will now present you a little bit of GitHub. So we used it basically because we were using Subversion, and before that, Mercurial. You don't want to know what is that. And it was just not enough, okay, because Subversion probably is good for 20, 30 users, but if you pass from that, you will want to have a lot of conflicts. And that comes from the part that Kratos is huge, and if you're modifying a part of the code that the other person doesn't use for anything, you can even break his code, okay, so it's something that we wanted to avoid. Basically, this is the industry right now when it comes to code development, okay, so even if you're not developing or end up not developing Kratos, you are going to use Git, either in GitHub, GitLab, or whatever flavor you want. Okay, so it's very important that you learn the basics of how this is going to work. And the good thing is that it can be integrated with many services. As you will see later, we have continuous integration, continuous development, and automatic testing. Okay, so this is something that is provided by you because the users of those platforms, not Git itself, but GitLab or GitHub. Okay. Another of the benefits of going with this methodology is that when you jump to the repository, you will see that you can create what is called a branch. Okay, a branch is like a section of the code or a portion environment of the code, for example, let's say, that in which you can work without affecting the work of everyone else. Okay, when you have finished to work with the feature or the bug fix or whatever you're trying to implement, you can then ask the repository to say, okay, I made this work, please integrate it and make sure that it doesn't break the changes that other people are working. Okay, so this is the main cornerstone of why we are using GitHub or why everyone is using GitHub, to be honest. It's also very quick to know what is happening globally. Okay, so as you will see, we can make an overview there. I will make a live demonstration on what is happening, for example, today in the repository. You will see all of this. Okay. Another important thing is there is a main branch in which you can ensure that if you load it and you compile it, it's going to work. Okay, it can be bugs as in the best families. Okay, but more or less we're sure that the things are going to work smoothly. And also it offers a place in which we as developers can discuss with other developers about things that we are going to implement. We can ask questions. We are not sure of the answers. We can tell problems or what we have detected. It's everything centralized in one place. So it's much easier for us as maintainers of the, for example, I myself am a maintainer of the repository. So it's much easier to have all this information centralized. So I don't have to start sending mails to people from Airbus to tell us, okay, what's happening in this problem or why did you block this solution, etc. Everyone is there. And everything is there. Okay. So when you enter, you will see something like that. Some of you, as I told you, already have read this. Okay. And basically, this is the main page of the project. This, you can see the branch, which is the master, which always works, okay, and the other branches in which people are working, okay. Now, in order to put something in the master, you will see that you will need special requirements that I will speak about later, okay. We have the pull request section, okay. This is when you make a change, okay. Instead of like putting it there without any other inconvenience, you have to make a pull request. Pull request is a way to say, okay, I made these changes to the code, I want to push them. Someone from our team is going to review it, hopefully fast, but it may take some time. If it's small changes, typically it takes like a couple of hours to be approved. If there are changes that are bigger or are in parts of the code that most people use, it will take longer. It will take up to a month, for example. So if you try to touch something which is in the core Kratos, expect this process to be long, okay? Also, if you want to make something, it must ensure that the tests are passing. Okay, so if you break something, it will not let you put the code that you've made into the available for everyone. Okay, so this is very important. What I speak about the discussions and conversation, when you make a pull request, you have a question or whatever, you can link parts of the specific code to speak about. Okay, so you don't have to copy paste something. You can just say, okay, this file from lines whatever to whatever, I have a question about what this means. Okay, you can ping it. You can put it. You can write normal code. You can ping people. Okay, so you are interested in that I, as a person, answer you a question. So you can put at my name. Okay, this also works for teams. So, for example, if you are interested in you are making an interaction with the fluid. Okay, so probably you will put at Kratos multiphysics fluid dynamics team. Okay, so someone from the team will be aware that this is an issue and will answer you. Who? The best person for that. Okay, so internally we will decide. Also, you put a snippet of code. So if it's something you want to reference something that is not in the repository, or say, oh, I want to modify this code with this other thing that I invented. It is good. It's not a good idea. You can put it here. People will see it in a beautiful format structure. Okay, so this is something that is available for you. And believe me when I tell you, this eases a lot the work of the code. Okay, so use this a lot. Internally in Kratos, we organize what we call repositories and teams. Okay, so there are several teams. One for every application that you will see in Kratos, and different repositories for different tasks of the daily life of Kratos. Okay, mainly we have 3 repositories that you will be interested in, which is Kratos, holds the code and the documentation for the code. Examples, which basically are where the examples are stored, and we divide it in two because otherwise it would grow, the main repository would grow too large and it would be just bad to download it and work with it. And we also keep another repository which is like a trash bin when we put images, videos, etc. Everything that is big and doesn't fit in the main repository and the example repository go there. Okay, so if you want to host an image for the documentation or this kind of things, you could put it there. We also keep mirrors in GitLab. Okay, we use GitHub as our main platform, but we also present another. Why? Because it, for whatever reason, Microsoft decides that GitHub has to shut down or whatever, so we have a backup mechanism. Everything gets mirrored there. Okay. And the important thing is that the repository is open. Also, it's public, but it's not open. You have to ask permission to be able to push them. Okay. Either working it yourself and making a pull request from an external repository, or directly asking me to give you permission to push things. Okay. In general, if you ask it, we will give it to you. So there is no, I mean, you can be nobody outside. If you ask me permission, I will put it. This is just a way to control people that have access to it. Okay, so we avoid people that tries to put spam in the repository, this kind of stuff. So no problem with that. Now, as I told you, in practice, there are like 3 repositories in which we will invest it, like Kratos, Kratos examples, and documentation, which is not here. We also have some which is called Git interface, which is for interacting with our own preamp processor. That preprocessor is not free, so I will recommend you not to touch that. It's just for internal reasons. Yeah, the interface is on, examples 1, documentation, like I showed you, and if you want, you can put external projects. So if you want to make a project which is not part of Kratos, but it's related to Kratos, for example, Manuel was speaking the other day about the utility that he had done for like converting things and clipping. If he wanted, he could have hosted it. Okay, so we have plenty of space to host projects your own. Okay, it's not the preferred way to host things, but if you are, if you need some space, we can put it here. For example, the GECKO simulation IO repository that I'm showing you here is a repository done by a guy which is named Philip Bucket, which allows interaction between Kratos and other simulation frameworks. Okay. So it's not 100% Kratos, but as it's very tightly related, we decided to use an organization. Well, just to show you here the evolution of Kratos. So this would correspond to the prehistorical age where we use subversion. The moment we started to use GitHub, as you can see, the number of commits and the number of contributions to the repository grow exponentially almost. So much better now. And with this, basically, we solved the problems that we have about having developers and not being able to organize ourselves. Okay, so more or less this comes from that. Another very important part, which is very related, and you will have to take into account, especially if you put or you want to introduce code into Kratos, which I suppose will be the case, is the continuous integration and continuous development philosophy. Okay, so in principle, every time that you make a pull request, you will make sure that everything that has gone before by the other developers is not broken. Okay, and we, not even me, can, well, as a lot of trust no one but me, good rule to follow. But basically, what I wanted to show with this is that we have automated systems that not even I, as an administration of the repository, can bypass. Okay, if it doesn't pass the test, it cannot enter to the main branch. So this is a rule of thumb. Okay. This also means that when you make any development, you make to make sure that you have tests for them, because it's a way in which you're telling the repository that from now on, this feature that I implemented, it's well tested, it works, and needs to be maintained by everyone that came before. Okay, so this is basically about what is this philosophy.
And do you have to test the code for yourself?
No, it's not automatic. It's not automatically. So I mean, it's good. It's a good practice that before uploading to a repository, you test it yourself and make sure it works. Okay, but the thing is that if it doesn't work, the repository will not let you pass. Okay, you will be unable. There are super corner cases, super strange, in which you can pull the CI mechanism and upload things. So nothing is absolute in life, so it's possible to break the system. It has happened, but maybe it happens once per year, or twice per year. Very low frequency. Okay. Now, the mechanism that we use for that is basically Travis CI continuous integration from GitHub Jenkins. There are many solutions. We use the one that is integrated into GitHub. Okay. But if you were interested for projects which are not Kratos, know that there are other services, which is not the one that we use, that are for the same function. Okay. Why we use this one? Because it allows you to test things in Windows and Linux. That's the only reason, to be honest. Okay. Now, this is basically the windows that you're going to see when a pull request is made. Okay. And you will see that in order to be able for this button to appear in green, or at least in gray, or not in black, is that someone has to manually approve your review. So someone has to tell you, okay, this is good. And aside from that, since we don't use humans, all the automatical tests need to pass. Okay, we have many of them. Some of them are, as you see, required. Some of them are optional. Okay, so for you to see that we are testing more things than probably are necessary, and we are not going to tell you nothing if you are breaking something that is super conditional about one problem, that whatever. We've had those in a separate environment. The ideal thing would be that when we pull request, everything is in green, but we are checking styling, augmentation, continuous integration. So we're testing a lot of things. Some of them are aware, some of them not. Try for all of them to be green. That's the message. Okay.
But this kind of test doesn't have to do with the quality of the code.
No. Well, some of them have, but they are not required to pass.
It's a clean coding.
Exactly. We have one specific for clean coding that tells you, okay, when you are introducing something that may cause problems or have warnings or are stealing problems, we have one for that. But in general, you can ignore that one. Okay, so it's super picky. Okay, so if you put two spaces instead of one, it's going to say, no, it doesn't pass. Okay. So it's very, but the important ones are those ones, okay? The ones that test the functionality of the system, okay? As you can see, we have a matrix of testing. We have what happens for Ubuntu in different compilers with different configurations. We test it for releases, for the book. We also test for Windows, what happens in Windows. We test for CentOS. And since Kratos, if you try to compile Kratos, we have noticed that it's super slow to compile, okay? This takes, I would say, around an hour to compile in the GitHub machines. Okay, we introduce something which is called unitary compilation. That's probably too technical, but it reduces the time, but it could introduce, or it could lead to passcode which is not 100% sure. So the core of Kratos is compiled with this performance mechanism and without it. Okay, so you can put the applications, but for the core, it's tested all the ways in the world. Okay, so you will not be able to pass something in the core which doesn't pass. Okay, we also test this for Ubuntu Intel. Okay, if you are compiling with the compiler, this is something you can also test. Okay, so it's very extensive. Be sure that if it passes, it will go. We also will test that it works for MPI. Okay, which is something that probably most of the users will not be aware. But if we detect that some problematic appears in your code because without running with MPI it doesn't work, we will let you know. Okay, we will let you know because you won't be able to manage it. Okay, so feel confident when you're working on code and don't be afraid to pull requests. This mechanism is there for ensure the quality of the code and also for else the developers to detect the issues. Okay, so I mean there's no problem about failing. Typically, when I make a pull request, it fails 100% of the time the first time. Okay. Also, if you go to any of these sections, you can check exactly in which section the code has failed, okay, and which is the reason, okay. If you enter, for example, here, you have setup build, which basically sets up the environment. It initializes all the libraries. You have a section for building the code, okay, and if there is an error in compilation, it will tell you, okay. It compiles with WVU all, okay, so warnings are treated as errors. As I said, super picky. If it fails running test, it will tell you exactly in which test, and you will see the message error. Okay. If it fails in any other section, you have running a small test, 90 tests, so tests are divided in different sections. It will tell you exactly which section and which was the cause of this error. Okay. There are errors which are very hard to catch. Race conditions mainly. that may bypass this mechanism. Okay, so from time to time, you will see that when you make a pull request, maybe there is an error which is not related to part of your code. Okay, in this case, please tell the person or the team that is responsible for that particular test. Okay, I had an error in the CI, please fix. Okay, so they will fix it typically soon. Okay, and basically with this, what we wanted to make is to ensure the quality of the code. So make sure that we are trying to sell your product or try to tell a university, okay, use our code for payment element. We have a way to demonstrate that that is working. Now, another important thing, and I'm afraid to say, this is very beautiful in theory, but in practice, we are not done, or we are not at the point we wanted to be. Documentation. How to add about documentation. So basically, the idea is that we have two separate documentation, which is in-code documentation, which is done by Doxygen, and external documentation, which is more theoretical, which is done by hand by the developers. Okay. The first part of Doxygen is more or less well done. Okay, so you can open any class in Kratos and you will see that every function is commented, everything. We can generate pages about those documentation. I will show you also later. It's already in the repository. The bad part is the manual documentation. Typically, developers are interested in like generating code to make this process work, but then they don't document what they have done, so it's impossible to know what their functions are doing or what they made that code. Okay, we have tried to make an environment in which is user friendly to make this documentation. Okay, and basically we're doing this by making the documentation as a code. Okay, we have part of the repository which is called docs, in which you have pages that you can write in Markdown. Okay, and this will be automatically translated to any system in which we want to show you. For example, the documentation pages, or if we want to make a wiki, these both resources that you have available. But the idea here is that you need to write the documentation in one point. We will take care to present it correctly, render it, so you don't have to take care about formatting anything. Okay, it's more or less like LaTeX, but adapted for GitHub format. Okay, so it allows you to put questions, tables, anything that you want.
And where is it in the repository?
In the docs folder.
In what?
Docs. I will show you when I finish the presentation. I will make a.
Okay.
Yes. As I said, this is like the always pending topic, so don't expect to be as mature as the code, but it's there. We are putting a lot of effort. So please, if you blow up something, take care to write documentation for it. Also, well, this is probably not very interesting for you, but I'm going to explain you anyways. How we handle all the process of releasing, making the code available. Okay, this is done with Docker. You know Docker? More or less. Okay, so basically, our infrastructure is built on Docker. Okay, every time we have to run a test, as I showed you in the CI, every time that we want to make a release, every time that we want to like deliver the product or something, we make it through Docker. Okay, Docker is nothing more than a virtual machine with the differences. Okay, in which we prepare the environment in which things are going to run. Okay, so we have basically, well, this is like the organization, but probably it's better if I show you here. Okay, so this is basically the infrastructure, the complete infrastructure of Kratos. Okay, so as you can see, Docker is in the center of it. Why? Because it's connected to repository. Okay, so it's the thing that we use to make the continuous integration and continuous development. It's the one that we use to make the Python packages. Okay, if you want to use Kratos and you're not a developer, you can just do if install Kratos modules and it will work. Okay, this is done also through Docker. It's the one that lets you deploy it in the cloud with Kubernetes or Terraform or whatever you want. As I said, probably not interesting for you at that point. And is the thing that allows you to make like releases, weekly releases, monthly releases, and store all that. So more or less, if at some point you're interested in the infrastructure or you want to copy it, just ask me and I will explain this one. More or less, okay. Also, this is important. I added just for you. Probably if you're in GECKO, this is an European project, no? So probably at some point you will have to make releases of the software that you have generated. Okay. Also know that Kratos is integrated with some tool which is called Zenodo, which was developed by the European Union. They tend to allow releases. So the software releases they tend to allow to do it with this. Okay. when you make a release with Kratos, or if you ask me, okay, I have to make a release for the European Union because the variable, whatever, okay, and you have the developments that you have done in the master, I just can click a button and then I give an ID, and you say to the European Union, okay, the software is in this DOI, and that's you don't need to write anything.
DOI?
Document of
Digital
identity.
object identifier.
See, that's it. But it's something that will require for the project. Just be aware that this exists, okay?
So it's a permanent link which univocally identifies the document it links to. So every article, for example, has a DOI.
Exactly. So this is a way to give it not an article but a piece of software. So you can reference, okay, my work is done in that specific version of this software. Okay, so you can link it. I mean, just for you to have as an option. If you don't want to use it, don't use it, but it's there. Okay, so basically this is more or less an overview of the project. Now, what I wanted to do is, let me see, just to give you like an actual view of, for example, the repository today, where I show you where all these things are located. Okay, so physics in here. Okay, see, as I showed to you, basically this is our repository. Okay, we have the repository sets of your we have Kratos, documentation, examples. Flow graph, maybe we can speak a little bit tomorrow if you have free time, okay? But yeah, important thing is if you enter, you're going to see everything that I told to you. We have the, for example, issues. If you have a question, you can put an issue. For example, the geomechanical teams, which is very, how to say, is very active in this section. They put things. So, for example, wrong application, press failure. Okay, so someone has detected that there is a fail or an error in the CI for that application. So they have linked this. He didn't make a ping because he doesn't know who to ping to. And one of the developers, for example, Google, is answering him that he's looking into it. Okay. And he also sends, for example, I found this in this pull request. Okay, for example. And why did he find it? So if you go to here and you click the X, for example, there should be one which is failing. Oh, okay, this is failing. So if you go to the details, in here, well, I cannot see because I'm not logged in. So let me.
Is there Carlos?
No.
Is it Carlos?
And the questions in the issues can be both related.
Sorry?
Can be both related to the code as well. You want to ask about some theoretical aspect.
Exactly, explain to me. If I can enter, I can show you better. Take my account. Okay, so in here, well, I wanted to show you here that you can go through the log, and it probably takes some time to load, but here it is. And people to insist on putting error in the name of the test. We should kill them. Well, then we have to look into memory. Oh, here, failed, for example. So you can see that in this case, the FCI application has failed. It doesn't tell you why, because it's a C50 test, because probably it has been a segmentation fault, but at least you know that it's failing. Okay, so you can more or less point to the people. As for your question, you can relate issues, pull requests, discussions, everything you want. For example, if we go to pull request, let me search for one of the super big ones. for example, this pull request here. So I was speaking to you about searching, for example. We have a library which is Policenter, which is more or less, it's making the interface for all the search structure better, okay? And it's making like among those pull requests. So as you can see, he's making a pull request, which is linking a lot of other pull requests. And we had a discussion about those. It will link it here. Okay? So you can reference, cross-reference, even in between repositories. So you can reference things that are not inside that repository. Okay. And the good thing is that if you want to reference one of these things, it's as easy as, so imagine that I want to make a new pull request for whatever reason. Well, probably better an issue. So the only thing that you have to do to reference it is to know the number of it. So try here, I want to reference 1, 1, 2, 3, 4, 5. We don't have so many. So just click here, and when the message is published, you are referencing directly. Okay. Okay. Also, as I told you, for ping people, just put a arroba or at whatever. For example, myself. Okay. So I can reference also groups of people. For example, if you want to ping to the design committee or technical committee, whatever, you can then, and they, if they have the notifications available, of course, they will receive something to let you know that there is an issue. Okay. So for example, from my point of view, if you want to see what happens, is from my side, what I would see, I see this. Okay. So I can know all the things in which I am participating, everyone that I've mentioned in the past, the things that I open, I'm not aware of, reviews that someone has requested to me. Okay. When I make a pull request, I can ask for a specific people to look at the code that I made. Okay. If I know that the changes are going to be related with fluids, because I will ask for a review from someone from the application. Okay. I will not ask from other people. No. As for the little bit, the structure of the repository, as I told you, okay, if we enter in the Kratos one, which is the one that you will use the most, okay, it's organized in different folders. Okay, we have the GitHub one, which holds basic information about automation, which files are ignored or which ones are detected when you make a pull request, that you can see. It has also information about owners. Okay, this is a feature that they didn't speak about, but the files, all the files in Kratos have owners. Okay, so if you make a modification to the file with an owner, that owner is going to be automatically pinged. So if you touch something in the code, for example, I will receive a mail telling me someone wants to make a change to that specific file. Okay, so if you forget to ping me directly, I will still receive that. Okay, and you will need an approval from me specifically as an owner of that file to merge the file into the master. Okay, so even if you have a friend, for example, I don't know, Angelo, you are very friend with Nicolo, and you tell, oh, Nicolo, please approve me this change. And I am an owner of file in which you have to do something, it's not enough. So you need to have my approval as well. Okay, and others safety mechanisms, so you cannot touch things that you are not supposed to, or without broken things. Okay. Also, we have issues, pull request templates. So the first time that you make a pull request, there's a template that you have to build. This is for easy to use as well. What else we have? Yeah, what I told you. The CMake modules folder, for example, this is something you can forget about. This is for compilation. The application. So in here you can see all the list of applications that are in Kratos. Okay. Now I will show you another quick presentation about the internal organization of Kratos, but you will see that it's organized with a core, an application. Okay, and every application works independently unless you want to link it with another, which is something that you can do. But every application has its own folder, and inside his own folder, it has his own compilation mechanism, his own classes, structures, etc. Okay, so the way to organize the code normally is in applications. Probably you will use the application. Yeah, sorry. And probably they will be interested in the application, for example. So you will go. Okay. Well, and more or less, this is organization of the code. Also, you will have the, just to show you, install. Okay, you have install instructions here in case you want to compile it. Some of you have tried already, but more or less, here you have examples, what you have to download. Please do not forget it. Well, a little bit of documentation. And also you have the main documentation repository, which is this COI, main documentation pages, which are linked here, okay? And more or less all the information about the documentation of Kratos. Also, it's divided into Kratos applications. So for every application, you have documentation. You have that available. For example, the structural mechanics in there. So as I told you, it's more like theoretical documentation than not documentation. It will show the capabilities of the application, where more or less you can find examples, things, references to the bibliography, etc., etc. Okay. For the Kratos part, it's going to be also theoretical, but more practical because the code itself it doesn't touch anything about physics. So you will have, for example, how to debug things about memory error, how to use GTD, make code profiling. So a lot of things you can find here. Okay. And more or less, this is a little bit the of the GitHub. So I don't know if you have any questions or.
I have a question for the previous. You talked about the interfaces for the processors.
Yep.
And you have a specific processor you use, or it's like.
So we have an in-house preamp processor which is called Git. The problem is it's not free. It's called GID.
Okay.
It's not free. So I suppose that if you request access to it, it will be given to you. But apart from that, we have interfaces for the Salome as preprocessor, and we can generate outputs for BTK, with Paraview or whatever tool that you have. Okay. So also we have something which is called flow graph, but probably I will show you tomorrow if you have time. It's basically another way to like generate not the exact image, but the structure for the problem. Where you see how. So this afternoon, Ruben will come and he will make a hands-on on how to prepare the problem. He will then explain you the past or the project parameters, the meshes, etc. He will dig more into this stuff. But yeah, you know what? We support a couple of C formats.
And for the automotive testing, yep, you have set up something like a schedule, or it's just.
No, it's every time that you make a pull request, it's going to be triggered.
So it runs on the background like in the night, and in the morning you see the.
No. It takes like, I mean, we have restrictions because we are in a public tier, so we don't have a specific machine for that. But usually it takes like an hour or so. So in an hour that you make the pull request, you should get the result of it.
So you don't run all the tests. Like, no.
Yeah, it will run everything.
All the tests.
Yes. It will run all the tests for 6 different configurations of relation. So it will run
like
the test. Sorry?
Like versions.
No, same version, but for example, you will run it, compile it with GCC in release, GCC in debug, GCC in Clang in release, Clang in debug, Intel compiler, Windows without applications, Linux without applications, and CentOS. And all of them have to pass. Otherwise, you can. But I mean, you can.
And this is implemented through Docker?
This is, well, it's implemented through the GitHub CI, which underneath uses Docker. So I mean, instead of like setting up the environment every time, we have a Docker specifically for that, which you can find in the repository as well if you're interested, which is in here. You go to scripts, basically these all the tools that are not outside, so things that we use. And basically here you have the configuration scripts, but there is a Docker files folder in which you can find all the Dockers for all the configurations. Okay, so the ones that are not standard, for example, the Windows one is standard. We don't use any particular library, which is not in the machine. That, for example, when we want to test CentOS 1, we have here the Docker description of all the operations that you need to run in that container before running Kratos. Okay, so if you want to represent in your computer or any other place, you can take the Docker field, build the Docker, and then use it as a prepared environment for Kratos. We have also Docker images with Kratos already loaded, but we mostly don't use them. But it's a possibility. If you're interested in having a Docker with Kratos already compiled in there, still ready to use, something I would have as well. And when we are generating releases, this is not part of the CI interface or the GitHub interface. We have a specific machine that also have a Docker infrastructure to generate all the releases except for Mac because we cannot visualize it. But basically, we have a mechanism in Windows that through WSL, it can like deploy containers of both Linux and Windows, which are in charge of generating the releases for those systems.
That was just the curious on the infrastructure.
Yes. So again, if for at some point you are in your projects, you need a release for Kratos because you have to send it to a customer or you need a deliverable or whatever, you can directly ask us, okay, I need a release for that project. Then we will generate it, we will give you the binaries or we will then upload it to the internet directly. So this is something in principle should not be responsible for you. So you can ask us and the only requirement is that if you want this to happen automatically, your application needs to have tests. Okay, we have to make sure that what you show that I don't have to spend a week fixing errors because it doesn't compile in Windows, for example. If this is the point, we will not take the release. But if you ensure that everything is passing, then no problem. We can generate it for you. Okay, so if you have another question, what I could do now is to more or less show a little bit the structure of how Kratos is organized internally and more or less show you which is the workflow of analysis stage, which Ricardo was explaining to you the other day. So you can see the specific paths in which this structure. Okay, so let's go for that. This is what about time? Yeah, well, half an hour, we should have enough time. Okay, so although this is a very quick presentation, this one is very important that you stop me if you don't understand anything. Okay, so let's go. Now, as I was telling to you, well, or Ricardo probably have mentioned before, Kratos is divided in two main parts. Okay, which is the Python layer and the C++ layer. In general, C++ layer fast and complex, Python easy and smooth. That's the more or less the thing. Okay, so if you want to implement something in Python, be aware that it's going to be slower. So, for example, you want to make a loop or the elements apply whatever thing. You can do it in Python for sure, but if you do it in C++, you're going to do much faster. Okay, so if you want to make a process, please do it in C++. Python, I would say that nowadays it's only for organizing the workflow and selecting, okay, I'm going to use this, I'm going to use that, but not use it per se. Okay, so just selecting like utilities, processes, solvers, but not executing them. Now, in the C++, also important that we have MPI extension. Okay, so both one and obviously each layer is divided in which is considered core and what are considered application. Okay, so core things would be the common things that everyone is going to use. So in the core, we don't have physics. We don't have linear solvers, builders and solvers, data structures, etc. But for example, if we imagine that an application needs an element, which is a tetrahedral, okay? In the code would be the definition of element, but not the definition of the tetrahedral. But probably a tetrahedral element will be in the code because it's super common, okay? But I mean, only the bare bones are going to be in the code, okay? And they are super optimized and with a fixed interface that you need to have a very good excuse to change. Okay, so in principle, if you need to change something that is located in here, in the repository, this belongs to Kratos. We are going to be super picky, telling you how to implement things, and we are going to be very picky about if they are efficient or not. Okay, so be very worried that if you want to make changes here, we are going to be very noisy about it. Okay, in your application, you in principle are taking there, so any change that you want to make, we are not going to tell you anything, okay? Unless it's core application. Now, as I was telling you, in the C++ side, let's say we have also MPI extensions. Okay, MPI doesn't compile by default, so if this is something that you need, you have to enable it specifically. Why? Because it adds a lot of complexity to the code. Okay, so if you don't want to use it, it's easier just to avoid compiling it because you need extra libraries to compile. You will need extra options when you're reading model paths to be automatically divided into partitions, etc., etc. It has a lot of complexity. If you need it, enable it. Yeah.
When you say that Python has an interface to the core, you mean that it's possible to access the core in C++ from Python?
It's not possible. It's possible to call it. So all the functions that you have in C++ or the things that are in a place which is called add whatever to Python, okay, you will see that there are a lot of CPP files there, okay, which are basically a stuff for function calls, which relates the function that you will see in Python with the function that you will execute in C++. I can show you. So if you go to here, for example, Kratos. In here. So as you can see, we have like a lot of add bounding box to Python and then GCL to Python, whatever to Python. Okay, so for example, let me open, no sé, add dogs. For example, the dogs. Okay, so in this file, you will tell, okay, you have the class dog, which needs to expose to Python all these methods. For example, get variable, get reaction, get ID, get solution step value, fix free, fix or not. So all these operations for this class are going to be exposed to Python. Okay, and we do this using the PyBind 11 library. Okay, so when you compile this and you import Kratos multiphysics into Python, you will be able to have the class dot, which will have all these operations. Okay,
So you will write dot and have the list of all these methods.
exactly. All of this will be available in Python. Okay? And what it's going to do is to get so it will get the parameters, it will make automatic conversion to the parameters that are in Kratos. So in this specific example, the name of the variable, okay, and it will call the C++ method and it will return you the result. Okay, but all the conversion between types, etc., is done automatically in most of the cases. There are a couple of exceptions. If you are passing arrays in this kind of structures, maybe it's not clear if it's going to make a copy or it's going to pass it by reference. Okay, so those particular examples, be careful, but in general, it's handled automatically for you. Okay, when you are developing code in your application, what you will have to do is to generate something like that for the classes that you want to expose to Python. Okay, and also it's important to mention that, let's say, even if it's C++, we consider those files to be in the Python layer extension, let's say, okay? Everything that we code in, everything that we code in here, okay, needs to be specifically exposed. So everything that we compile in here is in form of library, okay? And the interaction between C++ and Python is another library, okay? If you enter in a CMake of the application, when you see the code that is being generated, you will see that for every application and for the code, always two projects. Kratos core or Kratos Fluid Dynamics application core and Kratos Fluid Dynamics application with all the code, okay? Why we do this? Because the C++ part doesn't have access to Python in any way, okay? So you don't need, if you wanted to compile only the C++ and you didn't want to have an stuff for Python, you could do it, okay? So it's something that we do. For example, when I generate releases, I generate one release for the core, and then I compile every layer for every version of Python independently. So they are completely separated. Okay. That also means that if you're in the code, you cannot call Python to execute code in the C++ layer, for example. Okay. So the interoperability is only exposing symbols to Python. That's it. We don't offer any other functionality. And we strictly prohibit calling code from Python from inside C++. So it's always directional. That's all. Okay. Well, basically, this is more or less the structure. Okay, so if you have any question, tell me. Well, this is I should have removed that from there. Okay, so this is basically the most important classes that you will see in Python. Okay, in Python in C++. Basically, we have the kernel, which is the one that manages the lifetime of Kratos inside C++. The registry, which is where you're going to put all the things that come from the application. I will explain this in a little bit of detail now. Basically, all the, let's say, well, put here data structures that were explained by Ricardo the other day: model part, mesh, geometry, matrix, vector containers, special containers, everything that have been explained to you is available in the code and as a data structure. Then you have like the building blocks to say somehow, which is basically the variables that you want to store, elements, conditions, flags, degrees of freedom, geometries, multiple constraints, you have, linear solvers that you have, everything is stored there. Okay.
What specifically like in the container?
A
Container.
A container is like we are speaking about vectors, for example, later. So apart from this is a container, for example, a vector, because it lets you contain or store, in this case, proteins, doubles, whatever. We also in Kratos have specific containers which are for classes that we want, which are optimized for this kind of classes. Okay. So if you wanted to make a vector of elements, for example, we have something which is called a pointer vector set, that instead of copying the element into a vector, what it handles is directly that you will create a pointer which is pointing to that vector, which is referenced only once, so you don't have memory leaks, and it allows you to iterate it. So it's basically data structure to hold elements that are inside Kratos or entities that are inside Kratos, which are optimized for this kind of entities. Okay. But for example, in a way, a model part is also contained. Okay, it's more complex because it holds the nodes and it holds its connectivity, but it's not different than a vector in the terms that it contains something. That's just that. Also, you have input-output, dependent interface, obviously, and processes, utilities, strategies, etc. So everything that have been commented to you is inside your code. Okay? If you want to make your own modifications, don't do it directly in those classes because we're going to tell you no. The solution is deriving those classes and re-implementing the methods that are different for your specific functionality. That's more or less the idea. One important part is the registry, okay? So since we separate what we say the physics, which are in the applications from the code, we need a mechanism in which the code can be aware that those classes exist, okay? And we do this basically using a database, which we call registry. When you look at a process, when you create a utility, when you create anything that is named, for example, a specific element, what you're going to do is to go to the registry and tell, okay, this application has created this element. Here is a prototype of it. Okay. So when we are down to the code, we can take that without knowing that it's an instance of a specific element that we don't know and use it. Use it in the solver, use it in the builder, use it in a utility, whatever. Okay. This is mostly done automatically, so you don't have to be taking care of this. So this is internal of how Kratos works, but it's a mechanism that allows you to get a process that has been defined in an application and use it in your own application without having to have a dependency at compile time of the application. Okay, so the mechanism sends information. Well, this is basically what I explained to you. So we can skip it. Now, process and utilities. This is already explained yesterday when you were speaking what was the difference between process and utility. Okay, basically the only thing. Utility is a wildcard, you can use it everywhere, and it doesn't have any lifetime or anything in particular. Process has a life cycle, you can call it before initializing the step, after finalizing the step, or after executing before entering the solution. Before entering in the solution step, during the solution step, after the solution step, and after finalizing everything. So it has like 4 or 5 points in which will be called operations only execute, and that's it. So you have to put it in independent points. Operations, utility, and processes can be put in the registry, okay? Both if they are pure C++ or you have implemented it in Python. The only thing be aware that if you implement it in Python, you will not be able to use it in C++, obviously. But the other way around is possible. If you implement it in C++ and you expose them, you will be able to use them in Python. Okay. This is important. Why? Because mostly the process and utilities and operations will be used by the analysis stage, which is implemented in Python. Okay. So if you don't have the interface or you are not exposed to them, you will not see them. The good thing is that, for example, if you make a process and in your application, okay, in C++, you don't need to expose it because let's say the process class is already exposed for you in the code. So you don't have to do anything special. It will know. So the only thing that you will have to put is, okay, this process exists. You don't have to expose all the functionality. Just tell the compiler that, okay, I make a class which is derived from the process in the code. Please expose it to Python. Everything else will be done automatically for you. So you don't have to expose the executor before initialize or executing in live. No. all of this is automatically done. Now, so basically, the main workflow of the application, which is what I'm going to let you know, is divided into C++ and Python. Okay, and Python, basically what we have is an orchestrator which takes care of which the analysis stage is going to be executed. The analysis stage, which is going to take care of execute the solver and apply the utilities and the process. Now, the Kratos mine obviously is in Python, is called analysis stage, and is standardized. Okay, so we try to make it the more flexible as possible. Maybe you end up with a workflow that doesn't allow for to have an analysis stage for whatever reason. You can take the analysis stage and modify it as you please. Okay. Now,
what's an utility and what's process?
It's the same. So, in the from the point of view of the code, it's the same. Okay. From the point of view of the execution, the difference is that the process has places in which will be executed. Utility has not. Okay.
And also the interface of the process is fixed.
Exactly.
The interface of the utility is arbitrary. So in utility is a place where you can put the code you need to be put in C++. Okay. It can have an arbitrary signature because it will be you to call it, right? Whatever you need. It's like you want to implement a given function internal to your thing in C++. You put it in a utility. Okay. Now, a process is something with a very standard interface that is designed to be called at specific places in the code. So you'll have a list of processes, the ones you're describing.
Okay. So probably you will see clear why a process is a process now, and when you see why a process is a process, then utility is like everything that's not a process is a utility. Okay. Basically, that's the difference. But it's not something programmatically, it's something at the level of organization of code. So if you are writing code in your home, you can put your function, do whatever in every place you want. In here in Kratos, if you want a specific functionality which is not part of any of the workflows, you would put it in a utility and call it any way you want.
But both utilities and processes are in Python.
No, well, I in C++ and export it to Python. But if you can make an utility or a process which is pure Python. Okay? But those are the fewest because, as I said, they're going to be slow and you won't be able to use it from inside C++. Okay, so imagine that you have a mesh, okay, and you want to make a process, for example, that calculates the orientation of the normals. Okay, so you could do it in Python because you have access to your mesh and you have all the information that you need, or you could do it in C++. Okay, so if you do it in Python, you won't be able to call it in C++. If you do it in C++, you will be able to call it from Python or from C++. Okay, now if you do it,
Demonstrating the non-applications using analysis stage?
That's true when I was making this, but I think that now I use it. Well, IGA, there is applications that are still using analysis stage.
Maybe there is some legacy stuff, but
Most of them should
be using that. I mean, analysis stage is the place we try to put to standardize things. So an analysis stage, if you want, remember as a method run, and inside the method run, you can do whatever. However, the hint is that you try to do the things in the same way as the other application that we will do compatible. Okay?
Basically, what it does is what you have here. So this is the general view. It's not complete. I will enter in the details now, but you would have to take an idea of this presentation of today. I would say you please learn what's happening. Okay, because it's super important. Now, what analysis stage will do? And this is still Python. Okay, so we are not going to deep into C++. Never in here. First, it will create a SOP. So it will read the process parameters. Okay, and the first thing it will do when it's created is create a solver. Okay, it's super important. The first thing we'll do. Why it's super important? Because the solver will determine what is going to happen next. Okay, which process will be available, how the model part is going to be written, which variables is going to be used, etc., etc., etc. Okay, so first create a solver. This will come from the process parameters. You will see this afternoon. After creating the solver, we will add the variables to the model path. Okay, as if you remember yesterday, we were speaking about how variables store and etc. etc. We do it here because we need to add the variables before reading our model. Why? Because when we generate the model part, we are going to add those variables to the empirical database. If we don't do it, we won't be able to do it before, okay? Because it's not possible. When you assign the variables, it gets fixed in the memory. Now, once you have that, what Ricardo said, you can call the run function, okay? So the run function, what it's going to do is to initialize the life cycle of the process or the analysis stage, which basically is your simulation, okay? So first thing it's going to do is to initialize this. How is going to initialize it? First, reading the model part, okay? We have the variables, we have the solver, then it means that we can read the model part. The import model part thing, basically, will read your mesh and we create a model part and we put it in the model, which is unique for all the simulation, okay? If it's done in serial, this will call the serial code. If it's done in parallel, it will also take care of the partitioning the data for you. Okay, so you choose calling. Well, it will be called initialized. It will be partitioned for you if it's necessary. Okay. Prepare model part is a function that will execute all the operations in your analysis stage that need to be done from the model part in order to be usable. Okay, so imagine that. Also, probably not the best example, but imagine that you are reading an STL and you want to transform it using a voxelizer. Okay, so you would put that here, okay? Because the analysis stage, for example, you're telling, okay, I will need a model part, but in order to fill that model part, I will have to read as something that it's not MDPA, which is the native form of Kratos, make a transformation and put it there. That's something that you would put here. Okay. After that, when you have the model generated, you will call the add dots, okay? And this basically is going to select or fix the dots, add the dots. It's going to do this. Now, at this stage, we understand that your model is prepared, and what you can do is to run the solution loop, okay? As its name suggests, this is a loop, okay? You will find a finalize condition, okay? Until this finalized condition is not met, what you're going to do is to repeat this. And this is going to do initialize that solution, make a prediction about the result, actually solve the system, and then finalize the solution step. When you end doing this, you finalize and your simulation is done. Okay. Now, this is super easy. In more detail, these are all the things that are happening inside. Okay. So when you initialize, what you do, you create something that we call model. Okay, model is something that takes care of the geometry, but not of the model part. Okay, geometry modeler basically is something that is going to like read your geometry. Prepare geometry model is a function that will take care of making the changes into the geometry needed to be able to generate the model part. Okay, and set of model part is the one that is going to take that geometry, which has been already prepared and changed, and transform it into a model part. For example, another thing, I have an STL which have gaps, okay? So I would put here, okay, this is the function that will read the STL, this is the function that will fix the gaps and will transform it into a geometry, and this is the function that will take the geometry and put it into a model part, okay? If you have already an MDPA or a format that doesn't need those, you would leave those functions empty for your specific analysis stage, and it will directly jump to this function. This function needs to be done.
So if you're importing a geometry that is not very clean, you will be able to run it.
You will be able to run it provided that you put something that needs the geometry for you completely. But the specific place to put it is any of those functions here. Okay, so this is for reading, this is for preparing. So if you have to do any manipulation to your model, the place in which you would have to put it is here. Okay? If you say, for example, the generic analysis stage, these two functions are empty. Okay, but if you work in an analysis stage in which this is required, this is the place in which you have to put that. Okay.
Can I make a comment? One of the things that we're going to do later after the first will be to show how you can do some of those things. So in your main, you can modify, you can add something there, and these are entry points, what is describing for you to add some code, some user code. Okay? The goal is to have a unified structure. So it is very, very generic. There are a lot of empty goals right now, but these are places which will happen at a certain point and we can do your thing. Okay, that's why there are all of
Yeah,
those,
exactly.
even
So
if they are empty.
you will say that when something is empty, I will tell, okay, this can be empty or not. Okay. So, well, more or less this. Now, after this, what you will do, and this is will take responsibility of the solver. Import the model part. Why is this responsibility of the solver? Well, this is an open discussion because as it's implemented right now, it needs to be inside the solver because of the variable things. Okay, if not, it doesn't know who to read things. Okay, prepare model part will be the analogous to the prepare geometry model, but for the model part itself. So imagine that. I don't know, you want to divide the model part and you want to create a model part that holds whatever thing. Okay, you will do it here. So if it's not created from the MDPI file, you might make divisions. You might make calculations. Want to smooth the model part for whatever, it's the same as the model's prepared geometry model, but for the model part itself. Okay, so it's more or less the same, but for another data structure. At docs, as I commented to you, once you have the model ready, read all the variable sets, etc., it's the place and you're going to connect those. Now, modify initial properties, modify initial geometry. Basically, this lets you, or it's the place in which you are going to manipulate the properties of the model. So, Ricardo was speaking yesterday about that you can go to model part.properties that is a database with value. The place to feed it would be here. Okay, so want to make some custom, or you mark the properties, a table that computes whatever, you want to compute it in place. Put that code here. Modifying initial geometry, this is if you want to make changes to the initial geometry. So once you have read the model part, everything is in the slide, etc. Obviously, then you can make a manipulation of the geometry. Just for example, you want to change, I don't know that you will have to tell me this, Ricardo, but modify initial geometries if you want to change the type of the element that holds the
Imagine
geometry.
you want to rescale. Your model is made in meters and you want to convert it to milliliters or just to move for any reason, okay, just to change the coordinates. And that's what you could do it. Rescaling your model, for example.
Okay. Now, first occurrence of the famous process, okay? This will create, after all this has been done and your model is initialized, etc., we will create a list of processes based on the information that we have on the JSON in the configuration. Okay, so this will hold the list of all the things that are called process that you have in your configuration. And for every process that we have, we're going to execute the function execute initialize of that specific project. Okay, i.e. process. Sorry. So this is the first place when a fixed location of the process is being, okay, and it's just before initializing the simulation. Example of process that could use this entry point. You want to apply a boundary condition, okay, over a set of elements. So we have a process in the configuration which will be called Kratos multiphysics.processes.apply inlet condition, and in that process in particular, you will see that if you look at the implementation, the only function that it's implemented is execute initialize, and what we do is to look over the elements or the nodes of the particular model part that you are asking for, and it's going to do an initialization. So, for example, putting initial velocity, initial temperature, whatever. Okay, and the other methods will be empty. After that, what we're going to do is to call the initialize of the solver, which is going to take care to initialize the linear solver, put the parameters of the solver, selecting the strategy, selecting the scheme, etc. Okay. This, in principle, it's all controlled by JSON. Also, you will see this afternoon with Robert in the hands-on. He will comment you actually all the options of every solver and every linear solver there. After that, another time, we are going to look over all the processes again, and we're going to execute the function execute before solution loop. Okay, so if you need to do something that it needs to be done before starting the simulation, but after having initialized the solver because it needs information about the solver, you would put it here. I cannot give you an example right now of a thing that would fit in that specific position, but I don't know, imagine that you need the delta time that you have selected in the initializer of the solver to calculate something. Then the place would be here, okay? Now, if you go to list of the processes that are in Kratos, you will see that some of them have this function initialized. Okay. Also, it may happen that the process has this function implemented and also this function implemented because it needs to do different things at different stages in time. Okay. Once this is done, we have finished with initialized function, and we go to the run. Okay, this is the most complex one. Now, what we're going to do? Run solution step. Basically, what we're going to do first is to initialize the solution step. And again, when we initialize the solution step, we're going to loop over all the processes that we have, and we're going to call the function which is called execute initialize solution step. So this is going to be executed every time that we initialize a solution step. So imagine that the process has to reset a variable every time that we need to solve a step. So it will be interplaced here. While we didn't found until we didn't finish the loop, what we're going to do is to predict the solution. If we have a predictor, maybe this is empty, maybe not, I don't know. And once we have that prediction or not, what we're going to do is to solve the solution step, okay, after, which is going to be typically expensive. When we have the solution step run, what we're going to do is to check the convergence with the convergence criteria that we have set in the parameters. If it's not, well, and we will start the result somewhere, okay, and then we will call the finalize solution step. Again, there's another hook in the processes that will be executed when we finalize the solution step, okay? Once this is being called, what we're going to check is if the convergence criteria tell us that we keep running, we're going to repeat this lab. If we have finished with the solution, let's say, we're going to stop there and we are going to execute this anymore, okay? After that, what is going to happen is, well, no, sorry. This still doesn't finalize. So this finalizes the solution step, but doesn't finalize the loop. Now, before finalizing the loop, what we're going to do is to go, instead of the processes, the output processes. Okay, so output processes are a specific instance of processes that, apart from all the functions that I explained to you before, have another function that tells you when needs to be executed and, well, the condition in which will be executed. Okay, they will be executed just before the loop has ended, but conditionally, depending on the criteria you have to put. For example, you want to write every 10 time steps. So the criteria for the output process to be executed would be, we are in a step number 10, number 20, number 13, okay? You have several categories in which you can put this. I think that we have already implemented for time and for number of steps. So if you want to print every 20 steps, or if you want to print every 2 seconds of the in-time simulation. Also, you can put complex criteria there. So if you want to print every time that a specific node has a property, you can do it. It will be more expensive because it needs to be evaluated at every iteration, but it's something that you can do. This is basically the conditional. Also, the process themselves also will have another hook which tells you, okay, execute this before I'm printing something in the output process, or after I have printed something in the output process. Okay, same as before. For example, if you need to, you have your temperature in degrees and you have to pass it to kelvins only for printing. You will put it here for a process that does that. Okay, we'll print the output. In here, you will be able to select if it's for GID, BTK, or a custom format. I think that we support BTK, GID, and something for Siemens, those three, okay? And when you finish this, basically, we're going to now just evaluate if we need to continue with the loop or not. If we continue, we will repeat all of this for the next step. If not, we exit, okay? If you want to make more complex things like substepping and these kinds of things, that would be in the solve solution step, okay? But more on that also is afternoon. Now, when we finish, basically, also what we're going to do is to call the function finalize of the next stage, which again is going to call all the processes for the finalize function, and finally it's going to end. If we take all that we have done and we put it in the orchestrator, we will get what we call the multi-stage, which is nothing more than repeating all the processes that I told you multiple times. No, it's okay.
Actually, I have a question. What I'm not getting is, do you need to let's say, code all these
No, it's called by
steps in Python?
it's called by, so this is done, okay? When you call the run method in your main, this is automatically what is going to
So you
happen.
don't have to.
No, you don't have to write all of this. This is already done from this. Exactly. I can show you now exactly the file in which all of this is located, but you need to know that all of this is what is happening when you call the run function. Okay.
Okay, so you call the run from Python, and all this goes automatically.
Exactly. Now, it's important that you know that this is what's happening because if you need to make changes to the analysis stage, you need to be aware that these are the points that we can that you will be able to change. Okay. Exactly. So if you want to change, for example, you want to change and run solution loop for whatever reason, because you have a couple solver that first needs to run one solver and then needs to run another one. So you would go into the run function, but then you need to know that what you have to do is to call, for example, the first analysis stage function run and then do something and then call the other run. Okay. Or if you have to manipulate some results in the middle, it's important that you are aware that this is happening because if it's not as easy as call what's happening in the parent class, if you have to make more complex things, if you don't follow this scheme, it's not going to work because this is what the solver is expecting in the C++ layer. Okay. And yeah, basically what I was saying, if you merge all these and you put it in the orchestrator, you end up having a multi-stage, which is nothing more than first execute one analysis stage, and when you finish, you're going to execute another. A kind of the processes in here we have we call operations, which only have one entry point, which is execute before the analysis stage and after it has passed the analysis stage. Okay? Also important, when this finalizes, what it's going to do is take a snapshot of your problem and it's going to store it into this. Okay, so when you run a simulation, it's hard to stop in the middle of analysis stage, but it's super easy for us to serialize when it has finished an stage. Okay. So in principle, it will be done unless you tell Kratos not to do these checkpoints. So that next time you want to run a simulation, you will be able to start from the first stage, from the second stage, from the stage that you want. Okay, and this is also done automatically. You don't have to do anything. Okay. And yeah, so basically, this is I put them in here to show you more or less what you will see this afternoon. Okay, when you are running problem will be a file like this one. Okay, if you look at this, for example, you have our orchestrator. This is a station configuration file, which is the one used by Kratos. Okay, which typically always have a name, basically, which is the extension of orchestrator. Right now, there is only a test question orchestrator. Okay, which is when you finish one, do the other. For example, imagine that you wanted to run two models in parallel. For whatever reason, then you could create a parallel orchestrator. Manipulate the logic on how the scheduling of the analysis stage is going to work and use it here without any problem. Okay. Settings that you would typically use will be the echo level, which is basically the number of messages that you will see on the screen. Execution list, for example, because this is the sequential orchestrator, one after the other. This is the thing about making the checkpoints that I told you. So in this case, want to make the stage point and we don't want to load from a specific checkpoint, so we will start from the beginning. Okay, this is a folder in which you store everything. Okay, and here stages, which is the important thing. Okay, we will define the first stage and we will define the second stage. I will show you only one. I don't know if I can. So in every stage you will have all the information that will be written by the analysis stage, which is going to be the process of what is going to be done before calling that stage. Okay, in this step by the orchestrator. In this case, for example, we're going to call the import MDPA modeler. Okay, this model that you have there. Okay, this has the information of the specific configuration. When we create that class in Kratos, it will be filled with this information. Okay, operations. In this case, we don't have any operations because we don't want to execute anything. So when we run that loop, that will be empty. Okay, now which are the settings of the stage? So we are going to tell which is the analysis stage, empty analysis stage. This is an example because this is for testing and we don't want to execute any particular analysis stage. Okay, we specify here the parallel, for example, in this case, OpenMP. Okay, solver settings. For example, we will take the. So if you see that there are things that are missing, it will mean that it will take the default one. Okay, so in this case, we are not interested in which solver to initialize because this is a example, to test that one stage is run after the other, but we don't care what happened inside, okay? So in this case, we omitted all the information about the solver, that the whole one is going to be taken, and the only thing that we're going to enforce is that we're going to run with this test model particular, okay? We have a list of processes and a list of output processes, okay? In here, we would put all the list of things that we're going to be executed in those processes first, okay? Stage post processes, again, is what is going to be executed in the process, okay? It's called nothing in here. And if we look in the other stage, in here, you will see that we have two processes, okay? Because we're going to, no, we have one modeler, and yes, one modeler and one operations. Yeah, well, we execute the empty operation with answer, there's nothing, but we used to check that this operation is going to be called when we start the second stage, okay? And basically, I think that that's more or less the structure of how Kratos works in.
I think it's also a good moment to go to.
Yeah, so let me check. I think that I have nothing else. No, that's it. So basically, this would be the structure that your simulation will follow for any execution that you want. Okay, so always have this here. Okay. Behind this, or the same, the C++ level is where you will find, for example, you selected the solver. No sé, qué solvers tenemos, a block builder and solver. Then you will have to enter the C++ code to see how that solver specifically is initialized. So in here, it was only a box. In C++ will, so things will be happening, okay? The linear solver, the same, it will be initialized in C++, but those are the workflows. The one that tells you how the simulation is running, basically is.
One thing, will this presentation be available?
Yes, we can. Well, right now are not, but I send it to you.
I mean, if it's possible.
Yes.
Yeah, for sure. Everything is possible. Well, we didn't mention, but Kratos is completely open, so everything that, so it's open to the community. So anything that we do is secret, so you can share it with everyone.
That's good to get started.
Venga.
Yeah, but this is, okay, now it's one.
Tenemos
So let's.
IPL and Liga.
The idea to have these presentations for the next session, so we can.
Okay, I will manage. I will turn to Ruben to figure out them.
¿Cómo? Sí, ahora les decimos saludales. No, no. A ver, si me conoces desde hace cuándo. Para tomarla.
Con el látigo, bueno, para mucho, pero
no me digas. No, pero es el mejor de verdad. No sé. Que puede tirar también de verdad, que no va bien. Entonces, que si lo es que es
però di fatto dovresti farlo dopo che giocavi sono informati questi ok, cioè, questi dovrebbero deve essere il successo nel contatto questi diventano delle servizi no è vero sto avendo una il discorso è che non è vero che no, non è importante
I also have one of those, but I just have one. Toma, questo tratelo di spazio.
Luego, vale. Perfecto. Vale, sí. Adesso ma chissà pure we spoke about memory. Speak about memory and memory types, memory access. Okay,
Super.
What we yeah. Was this the presentation for Julian fitting?
Yes, it is. Well, there's some clear notes, but
Yeah, so then I know it.
But to try to put more example, but I didn't know if people make it super clear what we were using so many other structures.
We need to wrap one up.
Yeah, we should have more example, but I will do it. Si queremos conectar el portátil, hay algunos para.
El link. Uy.
Manuel has no. This is I can get all that. They didn't big one.
Yes, that is the correct this.
So now someone is
All'interno di attività durante le giornate mezz'ora il Vangelo su quello la domenica si va
tipo dove sono così, no, si stanno salvando.
Bueno, ahí sí,
Allora devo provare una variante. Ma io
Pero vale, entonces hay que ver cómo tienes sí, eso sí, pero no sé cómo tiene el tema.
Because I think you.
Bueno, ya
You guys, no, also one, right? Or no? Yeah.
But you will present the application.
For the second, I think you are supposed to go to Greece to the Thessaloniki. I mean, so the framework we are discussing, that would be to go tentatively March to June of next year. That would be okay.
And in the beginning of the year, but that's not a problem. The beginning of the trip.
Yeah, we take that guy. Okay.
But one thing, I also have a second that beta guy. I don't know if but maybe because Ali is not here, I don't know.
I cannot decide for you, so we will.
No, that's not okay.
We will speak. I mean,
Yeah.
sorry, our idea, because we
Wait.
are discussing with the professor with IT.
Mhm.
But I didn't speak this to your supervisor.
Okay, no, but
So
I
that's-
I guess the
I
most
will not-
like,
But not binding for you.
So we are just telling to them
Okay.
because we have a bit more control, let's say. Okay. They are proposing to try to have these guys to coincide, because this way we can see that. And since in principle, you two will be here next October for a video. That's the idea, so you spend a video here, and then we'll go back to Germany. And then we'll go but the idea is to have you there on the same.
Pero espera, porque me acuerdo de cuando lo que sería la. Ahí hay que darle al sol. Espera. Vale, pero espera. Vale, verás, porque entonces habría pero tienes razón, pero aquí hay un source.
I mean, I have to actually talk kids. The thing is that I came at university and we but I mean, I think if I try to get that program, I don't know, I imagine, you know, it's better to go to
Es que estaba medio por estaba como, pero, o sea, bailaba un montón. Sí, ay, lo que no tiene.
We are organizing our.
So, but I mean, still, we can make it like the inside, but the other 5 months at least, but the others are there, we should be easy to have here. We go like. No, otherwise I think going alone makes sense, but no, and also I think like working wise, like it's nice to like see going coming to for me at least.
I mean,
No, but okay, perfect. Thank you. Perfect, thanks.
I mean, it doesn't really matter because you will be working on different software. So,
That's also a big decision, but.
anyway, I'm gonna turn this to. So, by the way, this of Kratos brings maybe a.
No, I think it's no, Ale was also super positive about like also using it, so I think it's super nice. I mean, the more framework, the better. Like, I mean, that we know.
Yeah, we can get started. Yes.
Neon.
So shall we start, guys? Okay.
The break is not.
I think it was from the.
What was on the? Yeah, one of the coffee break according to the time.
No, but this is.
Yeah.
Three.
What time? Just.
But. So this is, no, this is yesterday. No, this is today.
They got the 60 volt, but it didn't tell me the copy.
Everybody is 50, so.
Yeah, we started a bit later.
So I think.
So maybe we wait. Now. No, ¿qué hora es? Son las 2:30. Okay, okay. So guys, do you have GED? I guess no. Some of you maybe yes, some of you maybe no. So you have the Mac issue, right? And Charlie is with you. So Charlie will set it up for you. And all the rest, you have GED installed? You have it? Who doesn't have GED? So, and you are Linux or Windows, right?
Yeah, Linux.
Linux is okay. So please go to the, because to set up an example, you need GED, okay? So go to this page, which is, well, if you put GID simulation in Google, the first one, okay? GID. You should see this. And then here, so here is the menu, okay? And in here there is GID for science, okay?
Is it possible to zoom a little? I think it's quite hard to see from here.
I guess so. Better, right? Yeah. Maybe. This is okay?
Yeah.
And then here in the load GID. Check the developer version, so we get the last one, okay? And in here, you have either Linux or either Windows. So choose the one according to your operative system and not drop, okay? So you are in Linux, Andrea, right?
Yeah.
So for the Linux one, and you as well. So you need to give permissions to use it as a program. Otherwise, you cannot execute the installable file, the driver. So right click, permissions, and you check the box allow executing as a program. Okay. And then you get the standard pop-up window to install it. Is it working or not? Did you want? So you're already downloaded.
Yeah.
Yes.
So go to the
Yeah, we were trying, but there is some.
let's click properties.
and then emissions, and below and everything at the top. Now, let's close it, double click, so now it should close. It should. Okay, and now you can start it.
I think also in wiki, license is not right.
Let me know when it's finished.
Yes, yes.
Esta ya no lo sé. Esta creo que no.
Soy chicano desde acá.
No, ya. Esta no, pero la voy a usar nada, un momento, para montar el caso y luego todo. Bueno, ya está, Andrea. ¿Sí? You as well? ¿El tuyo está?
Almost installing help files.
Okay.
Instalando las. Yeah,
ya estamos. So now open it as a usual program. So well, in the Linux case, you need to ask for the icons to be installed. So just go to the folder and navigate to the folder where you have installed GED.
You have the icons.
Ah, ¿te los ha puesto?
Los de la izquierda.
Ah, pues si te los ha puesto ya está, normalmente. Pues. If you have the icon, just click the icon to open it. If not, you go to this is for the Linux one, okay? You go to the GID folder, and then in the GID folder, as any program, you do /GID and below, okay? So you should see this once you open it. No problems, right? Yep. Right. Okay. Then, about this. First thing, this is in red because the license is not active, okay? This means that you have at most, I think it's 10,000 nodes per mesh, okay? So you can do small cases. About this, you need to ask your supervisors because the Git team, as you know, Git is not for free.
So normally your university needs to reach an agreement with TIMNE to manage this, okay? Just as a comment. So if you get this pop-up message, just mesh it with a cursor mesh and then store it. For today's exercise, it's more than enough, okay? But just as a comment in case you need it for the future. Then, now you have GED, but Kratos is not packed with GED. Okay, so in order to get Kratos, you have two options. One, to compile it, so you have your own version you can work with, edit, blah, blah, blah. And then you link that Kratos to the Python of your system. So each time you do Python 3 my script, you will be running with your Kratos. But you use GED only to set up your one. In any case, GED also has the option to get the Kratos from pip, as you will do by doing pip install Kratos, through this internet retrieve tool in here. So it's data. So in case, for those of you who already have Kratos compiled, you can directly use your Kratos. In case you don't have Kratos yet installed, do data, problem type, and then you can see that there are many problem types. And you do internet retrieve, okay? And the first one, in my case, is Kratos. With this, you get a module which extends GED to write the Kratos files, but also the Kratos, okay? So and in here, you do select the Kratos, you do retrieve module, permissions.
And once you have retrieved, how do you get, let's say, the newest versions? When there is a merge?
Each time we do a release, Charlie push it to the pip, and the GED always gets the last one.
But you don't have to do it.
If you do it like this, you see some Python packages required to be installed. So this means that we are ready. Charlie, te instalo todo, ¿eh? Luego ya te apañarás. So you see here in small, it says installing one Python packages, Kratos multiphysics, all 9.4.2, which is our latest release. So I repeat again, okay? Data, problem type, internet retrieve. And you get this window in here, then there is Kratos in the list, and you click again in the retrieve module, okay? Now it's installed. Any problem? Okay. So now in principle, we are done. We have everything we need, okay? In here, in preferences, if I'm not wrong, there is an option to select. No, it's in here. Let me check it. No, sorry. So let's go to data, problem type, and now in the list there should be Kratos because we have just installed it. So you click it, and you should see this. Okay. So these are all the, let's say, GED extensions we have to work with Kratos. Okay. This means, so these are the graphical user interfaces we have, but you have the complete Kratos. Okay, so you have installed the complete Kratos, but we don't have graphical user interface for it. Okay, so let's take, for instance, the thermal one, okay, which is the easiest. If you click in thermal problems, you see that you have standard convection diffusion, buoyancy problems, or conjugate heat transfer. Let's stick with convection diffusion. Okay. Then you can select the dimensions. Let's do 2D, and together with the GID icons, you should see these three in here, which is the Kratos. Is it working? Okay. Now you can see also an extra tab in here, which is Kratos. And in here you can see the particular Kratos options. Okay. So the versions, and in preferences, you can select how you launch your programs from GED. So you can switch from the version that you have installed from PIP
to the one that you have compiled eventually. Okay. So my advice, well, with people that develops in a daily basis, what I do is I have only the graphical user interface with no Kratos, no story, and I have my compiled version. So I use GECKO to set up the problem, and then I launch it from the terminal. And this is what Chaplitar, Vicky. So my advice for you, if you are developing in Kratos, do it like this. So you have only the compiled version. You don't mess with several versions in the team. Okay. Then let's say another thing that is quite interesting when you are learning is this window in here. So you see this string here. This is just to hide this. The rocket is to launch the problem. This is some information of the problem that you're running. This cross in here is to stop it. And this below, the one with the pen, it's examples window. Okay. If you click it in here, you can see all the convection diffusion examples that we package together with the graphical user interface. So if you click in here, you get something that it's ready to be run. Okay, so it's a sort of, let's say, prepackaged example that always works. So you can see, for instance, how do we apply the external flags? Okay, here there is external flag. Okay, I see this. Okay, so this is quite handy when you are learning. You try to set up your models and it crashes. You load one of these and you compare yours with this one, which should always work. Okay, this is quite handy for newbies. Okay, so let me just start a new one from scratch, easy one. So we play around a bit later. Okay, just to
this page.
It is in examples one. You
Okay,
mean?
but once you have the geometry loaded, how do we go back?
In new. Here, new GIA, as in what? The blank page. Okay. No problem, right? So let's create a super easy one, okay? So I will create a 1 × 1 domain and we set some boundary conditions and then those. Okay, easy one. So the cut of GID, it's a bit particular, let's say. So in order to learn how to use the cut of GID, you need to build models. For today, let's use this tool in here, the one with the blue cone and the orange cylinder. And if you click it in here, you can see that there is a square. Okay, so we can easily build a square. Okay, and then in the command window, you can put 0, 0. So the first corner of the square is the origin. And then you can put again 1 × 1. So you get a square. Okay, no problems, right? Good. And with this one, this is the extension room. Okay, so if you click in here, we get closer. No problems, right? I repeat again. Yeah. I will repeat it as many times as you need. So, or either I was there.
So just that to start.
And if you put now 1 × 1, so 1, 1, you get
So I think again. So like if I want the thermal before creating the
You can also do it like
okay, like yes.
first year of law.
Can I add the window from the thing? No.
Yeah. You don't need to start more.
Amazing.
It's sorry, but is it recorded?
I don't know. I don't think so.
Just to have access to it later on, like for us.
You just text me.
Okay.
Ugly or Javi,
Okay.
Ricky, okay. No. This is not a problem. So you have the square. Now, in here you can see the settings of the problem. So we can switch it, for instance, to linear. Or
Why are
linear.
we seeing two different squares?
This is because blue lines are the lines that you have in the model, and the pink ones are the surfaces. So if I change the render, here you can see that this is a surface. Okay, this is because GID is done like this. So it's the convention or the convention is that pink lines are the surfaces and blue ones are the this because okay. Now this is geometry. So let's start putting conditions and selecting the computational domain. Okay, to select the computational,
Which kind of analysis do we choose?
leave it linear, non-linear, it doesn't matter. For the exercise,
Thermal or structural?
thermal. Well, you can do the same with the structural. Now, in parts, you can select the material. If you double click in parts here, this appears, okay? And let's say, for instance, the density is 1000, conductivity, I don't know, 0.025, and the specific heat, 1000. Okay, so you have easy numbers.
So we can repeat the values.
Whatever you want, 1000, 0.025, and 1000. And then there is a select button, with a sort of brush, I don't know what it is. So if we click in select, and you see that the pointer has changed to a square. And now, if you select the surface, so check what I'm doing, it changes to red. This means that you have selected this surface to be this material, okay? Once you have finished selecting surfaces, you click on escape, and then you can select the name of the computational domain. Okay, let's put, for instance, domain. Okay. Is it working? Do you want me to do it again?
Yo me quedo congelado.
Sí. Sí. A ver si tienes algo de lo de la gráfica.
Error index. No.
Y ahora ábrelo otra vez.
Vale.
Ábrelo otra vez. ¿Listo? Well, once you finish selecting the domain, putting the values, setting the name, you click in OK, and then you can see that you have one new part in here, which is called domain. So if you call this tab, you can see that this is a material, a convection diffusion material with 1000, blah, 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 blah. Okay? Then, let's put some conditions. So I click in conditions here. This is for the boundary conditions. And you can see that we can put external flat or imposed temperature, or what we call internal thermal phase, which is for radiation and more complicated things, okay? So let's put, I don't know, for instance, temperature 1 in the bottom line and temperature 0 in the top one, okay? So I double click again in impose temperature. I want to put it in the bottom line. I do lines, and then again in select. I select the bottom line, escape once I have finished selecting my entities, and we put the name, for instance, bottom, this part. These names we put in here become the model parts of the Kratos, okay? And we put a value of 1, okay? Once you have finished it, you select OK. Done, right? So let's do the same for the top line as well. We call this one top, and we fix it to 0. Okay, so this would be both leading leg conditions. Okay, no problem. Right? You need to have here both bottom and total, bottom and total, bottom and top, and the slash total means that it applies during the entire simulation. You can create conditions from 0 to 10, and then another condition from 10 to the end. This sort of thing. Okay. And in here you have more settings for the strategy and blah blah blah. But let's discuss it them later on with the input files of Kratos. Okay. Then
what about the sides?
No conditions. Adiabatic conditions, doing nothing. So the flux will be 0.
If we don't apply condition, it's Neumann set to 0.
So Kratos will interpret that in there is no boundary contribution. So if you do nothing in your variational form, means that the flux is 0. So it's a weak symmetry condition. Okay? But you don't need to say this is a 0 flux, blah blah blah. Okay?
Hey, one question, can we check, for example, in this case, these conditions, can we check if we specify the right edge?
Yeah, sure. Yeah, thanks, because this is quite handy. So here you have, like in AutoCAD, the layers button. Okay, so if you click in here, there is another window. One is layers. These are the layers for the card. Okay, which in AutoCAD, the very same. So you can create your layers just to make the drawing more handy. But there is another one, which is groups. And in these groups, well, I have an extra one because I think I clicked it twice. So let me remove it. So you should see this, bottom, domain, and top. If you click one of them, for instance, domain, and you click in these 3 colored circles, this one, you can check which entity you have selected. Once you have finished it, you escape. Let's check top. Okay, top is top, and bottom should be bottom. Okay, it is highlighted below. Then let's save it just in case. For saving, this usual. Let's call it sample. And that's it. Now we need to create the mesh. For the mesh, GECKO has quite a lot of tools. You can do structural, linear, triangle, the second order triangle, no more than second order, quadrilaterals, blah, blah, blah. Let's use the default ones. So for meshing it, we do mesh, generate mesh. There should be this window in here with a predefined size. Let's put, for instance, considering that our domain is 1 times 1, we do, I don't know, 0.1. Okay, so we get around hundreds of elements, and you get something like this. Working? Then now you are in the mesh mode with this button in here. You can change the view back to the geometry, or you can, this one in here. In the left bar, the one in the bottom part. Okay? And then if you want to see the mesh again, you can toggle back to mesh.
Toggle geometry, mesh view.
Exactly that one. And you toggle from mesh view to geometry view and vice versa. Okay? And then now you have the model ready to be generated. And now you go to Kratos in here, this tab in here, the one corresponding to our problem type. And you can either just write the input files for Kratos. This is what we normally do. So, and then we run it outside the GED. And you can run it inside the GED. You will be running it with your Kratos. Okay. Let's do only write so we can check the files that we have generated, okay?
Is it possible, for example, to import a model from CATIA?
You can. So in here in files, you see import, and you can say GS, STEP, DXF, what a bunch of formats. Okay? Being transparent and truly honest, it is not mega super hyper robust. So for real engineering problems, maybe you import it and you need to fix it later. Okay?
We need to.
Fix it later on by hand. Okay? So they have put more efforts in different things, let's say. Okay, but you can import, I have done reasonably complex models, it works. For real engineering ones, well, it may struggle a bit, depending on the quality of the CAD that you are importing. Okay. Then, as I said, Kratos, write calculation files, no run. Okay. So now I have saved it in the desktop. So if I go to the desktop, there should be a folder with my case. This example.jd, in your case, should be the same. And if you open it, you can see a bunch of files. Some of them are only for GED, some of them are for Kratos. Okay. So the ones that are for Kratos, let's do one thing. Let me create a different folder. Eh? Yeah, but I don't know how to make it bigger.
Can you go back to the
Sure.
right calculation file in the run type?
Yeah, that one.
But we have to save the model document.
Yeah, sure. La resolución. Ah, bueno. Ah, vale. Pues mira, sí que se podía, no sabía hacerlo. Ahora sí. Échame, la verdad, todo Charlie. So let me create a new folder in here. Example to run, because I want you to distinguish well which are the Kratos files from the bunch of files that are created by GECKO. Because the Kratos ones are the ones that you really need to do simulations, okay? So just let me know when you are in the example.ged folder.
Do they have to be in the same directory, like both?
GED and Kratos files.
Yeah.
No, that's my point. So what I do normally, I create the model with GED. I remove all the GED files and I keep only the Kratos ones once I have the mesh. So that's my point. So if you want GED to do the mesh, once you have the mesh, you don't need the GED only to view the result, of course. Okay.
So you're just gonna copy from this.
Exactly. I want you to make clear which are the ones that Kratos really needs.
Okay.
Because in case you want to do the mesh with Gmesh, for instance, so you can do the same we will do here, but with your paper display process. Okay. So for the Kratos, in here we have what GED gives us. Okay. For the Kratos, we need the materials one. In the case of convection diffusion, it is called convection diffusion materials. In the case of the fluid, I think it's fluid materials, right? Or structural material, but materials whatsoever. Okay. Then the NDPA, which is the Kratos input format. The main Kratos, which is the main script. And the project parameters, which is a JSON file with the setting. Only these four. Okay, so you need for a standard Kratos simulation 4 files.
What's the use of the MDPA file?
It's the mesh. It's the I will open it just for you to see how it looks, but it's the input file, okay, for the mesh. So now let me open a code session here. New window. Of course, you can run the example in the original folder, but just to make things more clear, I prefer to do it that way, okay?
So you open the folder with the visual yes.
Exactly, because I wanted to check how they look like, okay? Ready?
Yes.
Okay.
Well, I mean, yeah.
Ready? Okay. So let's start, for instance, with the MDPA, okay? So in the MDPA, you can see some legacy stuff in the beginning that we have to give support to people which is still using legacy versions of Kratos. Forget about this, okay? But in line 8, you can see that it is a standard finite element input file. So first, coordinates of the nodes. Then begin elements. In our case, we have standard triangular 2D, 3N elements. So ID, the next column in here is the property. So the materials that we will assign later on, and then connectivities, okay? 1, 2, 3, and okay. And then we have what in Kratos we call it conditions, which are the, let's say, so we have elements that do the volume integrals, and we have something that they call, when they will jump conditions, to do the boundary integrals, okay? So these conditions are line elements in the boundaries that we have selected. In our case, we have bottom and we have top, okay? So the preprocessor creates these elements just in case we want to impose a flag or whatever.
And the number you have there are the connectivities of those.
And these are the IDs of the conditions, which are not consecutive to the element ones, and these are the connectivities. So this means that we have a line from node 1 to node 3, okay? And then we have what we call submodel parts, okay? And this is especially interesting because this you will use it a lot, either in the context of IGA or in the context of standard finite. These are our colors. So the coloring of our mesh is not like this. So remember that, for instance, for the volume, we decided to call it domain. So the GID interface puts a prefix in front, and then the key that we have put in there. This you can change the naming here. If you want to call it my domain, you can call it my domain. When Kratos parses this file, you will have a group, we call it submodel part, a group that collects all this set of nodes with all this set of elements called domain or my domain, or in this case, CNVDF parts underscore domain. So you can navigate, take that group, and do whatever you want with those elements. In our case, we will assign standard thermal elements to this group in here. Okay?
In this case, we just have one submodel part for the model part.
We have one submodel part for the domain, and we have two submodel parts below, which are, so these are the nodes of this submodel part, the elements of this submodel part, and then we have a submodel part for the bottom line and a submodel part for the top line. So the structure of our, when we parse this input file, we will have a main model part, we call it main model part, which is called, in this case, thermal model part, I think. I will show you later on where do we set this name, with some model parts, CMVDF, I think it was something like this, domain, another one which is impose temperature to the top and the same for bottom. But don't get confused with this. These are only names. So this is a name, a label. You can change it. So this doesn't mean that you are enforcing any boundary conditioning here. But GED, because internal reasons for them to manage data, they do it like this. But this is just a label. Okay, you can change it if you want. So this is the structure of our input for standard finite elements. As Manuel told you yesterday, Enrique has told as well, for the IGA you have this JSON file with the integration points and blah blah blah. So it's slightly different, but the concept, the submodel part still remains. Okay.
I'm sorry, could you just repeat again, what did you write on the board?
So this is the name of the father model part, the one that groups everything together. In this father model part, in our case, in this example, we have the domain one, which is the surface, the bottom line, which GED decides to call it impose temperature underscore the username, top, and the other one for the bottom line. Okay, but what I was telling is that this impose temperature to this is just a label. It doesn't mean that we are imposing temperature. This is just geometry, no boundary conditions yet. Okay. Then this is about the geometry. Then we have the materials, which is nothing special. We have the name of the model part to which you want to apply the material. In this case, the parent dot the sun, which is domain, and the values that we have set.
Why the materials aren't included in the project parameters?
Because we want them to be separate. Because we want the project parameters to be settings at the end of the day. Settings and boundary conditions, and materials to be separate. This is super easy material, but you may have component materials, multi-layer. So you want to have a super complex material with super complex JSON aside of the setting, because otherwise it gets super complicated. But this is a design decision. We may have decided to do it in a different way. Okay. And then the settings JSON. This is the most probably the most interesting one for you. So there are a few main blocks in this JSON settings file. Okay. And this is the same for IGA, finite elements, any simulation in Kratos, any single stage simulation. Okay. You have the analysis stage. I think Charlie told you about this morning. So this is the name of the Python module that you will be loading to run this simulation. Kratos multiphysics dot the submodule of Python. As Charlie told you, we organize our Kratos in submodules depending on the applications. So each application of Kratos has its own submodule. And then we have the convection diffusion analysis, okay, which is the analysis stage for running thermal related simulation. Okay. Then you have problem data, which is, let's say, general data like the starting time, the end time, the name that you will see in the terminal when running the problem, this sort of more general data.
What is echo level?
Echo level is the verbosity of when you are running the problem in the terminal, the verbosity, or the amount of information that you get when checking the terminal. If you put 0, you get low level of information, so you can more or less follow what's happening there. I think it's only the step you're running, and the warnings, of course. If you put 1, you get the convergence of each nonlinear iteration. If you put 2, you get some extra timers. Up to the level that 3, I don't know what 3 does. Honestly, I never used 3. But if you put 4, it's the maximum verbosity, and it gives you the left-hand side and right-hand side of the problem in matrix matter. So you can debug. Okay, so it's the level of information that you get when running the problem. Okay, this is the echo. Call it verbosity if you want.
Can you comment a JSON file?
You can comment it
It's //
like this. If you do like this, actually later on we will comment it to do some tests. But if I do like this, it is commented and it works. Okay, // You need to be aware of the comma, of course, because if you commented this line, for instance, you need to get a comma, but this is okay. So speaking about the blocks, so there is this general data, problem data. Then there is the solver settings. So I think Charlie explained a bit about the solvers this morning. So this is the information that you want to get into your Python solver, which is the one taking care of the physics. So this is, for instance, in here we will see the linear, non-linear, these sort of things, tolerances, and blah, blah, blah. Processes are, Charlie explained the processes this morning. Okay, so it's the way that we need, or that we have to communicate what the user puts. For instance, our boundary conditions will appear in here, and then we have the same for our process. Okay, so I want my simulation to be printed in paraview each time step. This sort of information goes in here, and this is for the restarting. Okay, in case it crashes, but these are more advanced. So as I said, there is this problem data in here. Okay, the name of the problem, we call it example, you can change it to my example 2 or whatever. The parallelism, open P and PI, the time, the end time, and these sort of things. Okay, solver settings, so for instance, transient, stationary, linear, non-linear. The name that we want for our main model part, by default, we provide one to the user, but if you want to call it, I don't know, Charlie model part because you want, you can change it, and your model part structure would be Charlie model part, domain, top, and blah, blah, blah. Okay. The input file, so this is the MDPA we are reading, example MDPA. The materials you are reading, so in case you have multiple materials, you just need to change it in here to 2 or whatever. The echo level of the solver, so you can have an echo level for the whole simulation and an echo level for the Newton-Raphson, for instance, and some extra settings like tolerances, these sort of things. Okay, and then if we go to the processes.
Why do you have linear analysis type and I have non-linear?
Because you didn't change it I changed it just.
Can I change it?
Yeah, sure. If you change it in here, you remove the non-underscore and you will be running it with the linear strategy.
So it should be stationary linear.
Yeah, but you can run it with the non-linear one. It will work. Okay.
It will converge in one iteration.
Yeah. I changed it in the GECKO just to show you how you can change things. And then in processes, since we said no initial condition, so there is nothing, but we have the constraints process list. These are our 2D boundary conditions we set. So in this case, we have a process in Kratos. There is a bunch of processes. I cannot explain all of them to you today, but the idea that you need to get is that there are some processes to do things. So the message is, Ricky, I need to do this. Okay, go to there and take that process. And then you check in implementation which are these parameter settings for that process, and you fill them according to your needs.
So a process is a kind of function.
It's more than a function. I would say it's a functionality because it's something that gets executed at some points of the simulation. Which points? The ones that we decided to be executed. For instance, this will be executed at the beginning of each time step. So at the beginning of each time step, we will be setting in the bottom line the temperature to 1, and we fix it. So there is constraint. So this means that the degree of freedom is fixed at the boundary condition, and that we want to do it from time 0 to the end of the simulation. Okay? There are other processes. Maybe you want to just set the temperature to 10, but not fixing it because you want it. So you set this to false. Maybe you want to set from 0 to time 1 the temperature to 1, and then you can put for instance, if you want, you can put a linear function like this. So you can do these sort of things. So imagine that I want my temperature to be equal to X. Well, now the braces are, I messed all the braces, but you know what I mean. So I can do this, for instance, I set from 0 to 1 the temperature to X. So we can put functions in here, Python interpretable functions, and then from 1 to n, we can set it to 10, for instance. Okay? So the message is that if you put things in here, you get them executed at some points of the simulation. And we mainly use it either to output things or to providing boundary conditions, okay? Or initial conditions.
Can you give another example of a process in Kratos?
Yeah, there are a lot. Maybe later on, if we have time, we can do a short CFD one, and there will be an inlet process, and you will see that this block is the same, but this is slightly different because an inlet behaves different to fixing one page. Okay. And then there are this list. You can do the lists that you want, but these are again a bit more advanced. So let's leave it for the future. Okay, but you can have in here another list. My custom list, and I leave it empty. So this will work. Okay, you can put as many lists as you want. So you can organize the processes according to your needs.
So
And
these are 3 processes in the.
Exactly, we have in this constraints process list, we have 3 processes in this list. And the one thing that is important is that these are executed according. So if you put these 3 processes in this list, they are executed in this order. Okay? So this is important. Because maybe you want one boundary condition to be applied before the second one because one overlaps the other. In the sense, for instance, if you have a corner, this node is shared. So you need to be aware of this thing. So we give the flexibility to do whatever you need. Okay? And finally, similar to the standard processes, we have the output processes. So by default, GIB writes a list with the GIB output and one with the BTK output. You can deactivate either one or the other in the interface. If you don't deactivate them, you get both BTK and GIB output. Okay?
And this process is going to be executed at the end.
Exactly. This is why we put the output ones separated from the boundary condition ones, because the output ones are executed once you have solved the problem. There is a point of execution which is execute before solution loop. In case, imagine that you want to multiply the temperature by just because you want to output it in that way, or to normalize it. You use that point of execution, then you call the output, and then you call the finalize of the step. So you may clean up your strategy, for instance.
And in the case you have an unsteady problem,
Mhm.
each time step, the solution is written to the BTK or at the end of the whole simulation.
At each time step, you write so you can select it. So for instance, let's check this one. So in here, you can see that you can control for the J, and this is the same for the BTK one, to write each according to the time. So in this case, I will be writing after 12.5 units of time. Kratos doesn't have units. So if you set your simulation is hours, this would be hours. If your simulation is seconds, it will be seconds. So you need to work in a consistent system of units, the one you like the most, okay? Or you can set step, so I can write my output after each 100 of steps, okay? Is it more or less clear? Or at least the overall idea? So now, the last one, The last one is the main, which is the script that we use to run the simulation. Okay. So if you open the main script, which is called main Kratos.py always, you have this. So let's start with the part below. So you know Python, no? At least a bit of Python, all of you, right? So if I execute this main Kratos file, I get into here. As you can see, we are reading the project parameters JSON, okay? And then in here, we are creating, we import the module, which in our case, remember that it was this module in here, Kratos multiplication distribution, blah, blah, blah. And we are creating the simulation, okay? Before this, we have this model. This is a container that we have in Kratos to store all the model parts we have. So on top of this one, imagine that imagine an FSI problem. Okay, in an FSI problem, you will have a fluid model part, which is the CFD problem, and a structural one. So this model container for a CFD will look something like this. You will have a fluid model part, which is the main model part for the CFD solver. And in here you will have a structure model part. Remember that the names are up to you. And hanging from these model parts, you will have, I don't know, inlet, outlet, walls, whatever you need for the CFD. And in here you may have, I don't know, loads, support, or whatever you need for the structure. Anything you need. But in this model, you can have as model parts as you need. Okay? So this model contains all the geometry of your simulation, let's say.
And why are you calling this function with no argument?
Because this is the constructor. We are creating an empty model, you see global model, and we pass it to this function we have in here. This function gets the module of the analysis stage, in this case, convection, diffusion, blah, blah, blah. This empty model, which is empty, because we have just started, and the settings, which are the parameters that we have parsed in here. And in here, there is this function we are calling, and we are doing a trick in order to flash the terminal with a reasonable period. We are creating in here the derived class of the argument we are passing in here, which is my convection diffusion analysis. Okay, this is a trick. We are extending the module that solves the thermal problem to do this flash. This is just a trick. Okay, is it clear more or less?
Do you need to remember all this when you write a code in Python?
You will remember. If you start working in Kratos, you will know it by heart, really, because this is a daily basis. And it's, I would say, the Python layer is reasonable. For all of you, it will be easy. Believe me, I'm pretty. Or you can ask, for instance, Nicolò, Andrea, Politeam is getting acquainted already, and you have started in September, right? So 3 months. Yeah, we are in January. Yeah, 3 months with holidays, and he is more or less familiar, or at least a bit familiar with this. So you are very familiar, and you have started maybe 6, 9 months with the master's thesis. So it's easy. The Python layer is easy. Okay. Then for running it, I will run it with the terminal. ¿Tienes PowerShell, Charlie? Charlie, ¿y dónde está? Ah, vale, sí, ya lo veo.
No, las terminales normales, si abres una, es PowerShell.
Ah, vale. So let me go to the, no, Carlo. Desktop, delete test. I call it example for run, no? Yeah, and here if I do Python 3 exe, my Kratos, qué bien.
In Windows just one, no Python.
Ah, yeah, verdad. Python without the, but we do without the free.
Well,
Without the, so I normally work in Linux, as you can see. So it should work. If you have everything compiled, so open a terminal, go to the folder, Python.
They have to export.
You need to set the environment variables, most probably.
When you are in the folder, you have to.
The one we created only with the files that we need to run. It works? This is working for you. Are you in that? No digas
Where is it?
No, you have just to.
but if you install it with the Charlie, isn't this automatically done if you install it with GECKO?
If you run it through,
Only if you run, of course, if you run it through GECKO, yeah.
Yes.
You compile it by yourself.
Yeah.
Okay. Then you need to set environment variables for sure.
yeah, exactly. But I mean, it's just this is out of
So is it Kratos
I can do it because I have not compiled the thermal application. I have FSI, but not the thermal.
Well, so if you compile it, it's a small one,
our business on the
a few minutes, or you do a structural one. It's the same.
open this.
What's the name of the
It's convection, diffusion, application with capital C.
No, it's not my name. That's just convection application.
What exactly we're doing?
Just the thing.
Is setting now that we are now.
You are saying to Python, where is your Kratos? Where is your Kratos? You're setting the environment variables. Because otherwise, like the Python is not aware, and you have this Python.
It's not that
No.
Because they have to do the same, they need to combine Kratos by myself.
If I compile it, I have to start well, but by doing this, you are extending your Python path. You also have to be aware of this.
Vale. Entonces, por ejemplo, ahora tendría aquí al texto. Y ahora tendría esto. Vale, y entonces ahora CD.
Because you said the.
Y ahora Python 3.
No, yeah, not only yet. Show me your your compile.
Yeah.
No, io intentando accedere in avanti, vale, perché è cambiato qui, sigue utilizando el punto para es una
The same stuff.
Now you are compiling.
Do you have that?
So if you right click in the new file and you open it with Visual Studio Code and see entonces la bash esta es
posible, pero bueno,
vale, gracias. Okay. From
The verification you did yesterday,
Yeah.
they were in the,
tiene la convención de Houston, que no la tiene compilada.
okay, yeah.
Uy.
Okay, because we work with the structure.
Well, what I know that in this case, this is why you need to create like the IGA class.
I did it. It says that because if you run only the Kratos or the daily of the strings, it flashes maybe after which flashes like when you have at the same time you're running. So this generate then increase once you have finished the system, you publish you get that information. If you are compilers, anything information you can access. The number of steps, for instance, create a super string, and once this string reaches the line, and then you get a white string, then white string, then room. You can set this flashing event yourself. So we ask the Python for that information in the
yes,
and this is for the user to see that, because otherwise you think, okay, this is stuck until point, because you get still like this, and then you go from that way to make it more.
So it's just for the purpose of visualization.
That, and not this one is this one is something that is okay. But we know that there was people think that it is stuck at some point, it's not working, something wrong, there's a memory leak. So if I'm doing this, you are listing, let's say, constant flow of changes in the code. Okay. So is it running for all of you? Exactly. So now, in principle, if you open GID again, or in the, you can switch to the post-processing with this arrow. And in here we should see some colors. We open our example. So are you in the post already? Yeah. So if we go to the one we are run, it is in my case in users, Roach Carlo, desktop, example to run. And in here you can see that you have both GID and BTK. Okay. If you open the GID one, you can load the results. And there is what some temperature in here. Okay.
Did you have something?
Run the thing, open the results. You get like GIT and BTK, and you get GIT. We can get all this. So we just run the thing.
Apparently, configuring was in
Then when for example to run GIT, you run
Porque luego en teoría la.
maybe, but you were there. Yes, you need to run it, and then I upload the solution. No, I think maybe very.
Es que aquí hay que yo hablo luego. Vale, son
I also have another project tomorrow, almost full, so I think I can wait. Yeah, I can wait my study tomorrow.
But if it's too much,
So
you think it's a good idea to freeze them in
in 1 day.
So let's do this.
So today I think you can.
We think
You
you
make
make
a
this,
big
we upload, and
Because then tomorrow
make
we'll
sense
make
from
my
the
video.
But just, it's okay.
It's okay, yeah. And you guys
If
got
it is
the
okay
idea.
to you, fine.
Because it's important, otherwise they will not So I'm going to explain the difference between this implementation or some and the
So,
and then we have in the object because that was
right, okay.
then this is also the difference.
So let's do it like this. So we finish with this and then we choose.
Exactly. I have these sessions together with the goal of one session.
Okay. So let's go to the coffee break. No? So guys, we do the coffee break and then we continue tuning a bit the simulation in the next week, which is something quite handy. Okay.
Is it possible to go over all the instructions in the iPhone to understand them?
We will do it later, okay? So Ricky, let's do this. I go through the stages of the stage and then tomorrow you say, okay, for the IGA, we switch this one.
Exactly.
Let's do it like this.